consent. So the first presentation this morning will be by Professor Van and I. She's going to talk about our education and community outreach. We'll have an update from Shilling Pei, Andre Barbosa, and Jerry Ryan on the Talbot project. I personally was very impressed to go up there. That was, I think they finished the 10-story a week ago or something, 2 weeks ago. So we're at the right time there to see everything constructed. We'll try to make our full break today instead of having a short one like yesterday. After the break, Michelle Morrison and Gilberto will talk about the modular test bed building. This is an option available for people to put onto the table to test different design details. And then Adam and Sandri will talk about the Sim Center tools. Baruch will talk about the IT resources. And then I hope we still have some time at noon to have some additional Q&A. I think we had a pretty good discussion yesterday after yesterday evening. So I'd like to invite Joel to come up. Oh, Joel, do you want to say a few words?
Yeah.
And I'm very sorry for not being able to do it. And personally, really had that I have COVID. And wish you a great day. Happy with your peers and see you.
Thank you, Joel. Joel, could you? Baruch, does somebody want to start recording? Okay, Joel, can you start recording so we can record all this presentation?
Sure. One second. Yes, I just started.
I think you need to add Robert's computer.
Yes. Should work on it. But if it doesn't work, actually.
But I've been involved from day one of developing the proposal and everything. But I know we're going to keep this short. I know you want to get to some of these other presentations. We all know how important education and outreach is. We also know that it's kind of on the peripheral of the amazing work that's being done at different research facilities. What I wanted to do was basically show you what our goals are for education and community outreach, and then talk a little bit about opportunities if you were to write a proposal or something to leverage some of the stuff that we're doing here in your proposals as potential broader impacts and things like that. So, no, didn't like that. So yeah, so we'll talk about goals. We'll look just at the different partners that we're working with and give you some just really high-level ideas. And I'm here also. I've made my career I was switched from bridge design to education, so engineering education, not only at the college level, but I'm like right now I'm going to take off and go do an outreach event with middle school students and stuff. So this is sort of my thing. And if you have any questions as you're putting proposals together of how you might be able to integrate some creative things, then feel free to reach out to me. And then I just wanted to put a plug. I'm not going to show the survey link, but at the end of the day, we would really appreciate if you guys take the survey for the workshop because that's how we improve it as we go. For a couple of years we've been remote, so it's really great to be back in person. But we also want to get your feedback on the schedule, the agenda, the presentations in general, the logistics. So thank you. Okay. So we we have about 5 or 6 goals for education and community outreach. The issue is that we're trying to address a lot of different stakeholders. So we have the researcher community, like you guys, that are very important potential users of the site. We have industry partners, we have just general public, we have our sponsoring agency. So we're trying to find a mix of things to target the different stakeholders. One of the goals is to support technology transfer for practitioners. So basically, how do we promote getting the research, the dissemination of our research results into the community, into codes. And this is accomplished through workshops. So not these kinds of workshops, but more like industry, academia, collaboration types of workshops, webinars, and I'll talk about that in a little bit, and attending different conferences and discussing the potential of this facility and the results from different researchers. We want to highlight a lot of the research that we do here at the site, and I think Joelle in the very first presentation yesterday mentioned the Jacob School Media Relations team. And I may mention it again, they provide a lot of support. I think Dr. Pei will be able to address that as well in terms of how to get the word out there through social media, through events with the media about your research. And so we help connect you guys to this resource for you as you're doing research at the site. We want to engage K-12 students into understanding earthquake engineering and really getting them excited about the potential to do structural engineering or geotechnical engineering as a career. And we target a lot of underrepresented minorities and socioeconomic groups. And we have a lot of partners, great programs already at UCSD that you can leverage. And I'll talk a little bit more about that in a second. We do want to provide professional development for undergraduate students. So some of our students that can participate in some of the programs that exist at UCSD, there's a Jacob School of Engineering mentorship program, a Cosmos program, which is a great way for undergraduate students to participate, to teach high school students engineering, and then other different research opportunities for undergraduate students. And including the REU program. So if you're all familiar, NHERI has its own REU program. They send 3 students to every site every summer, 2 to 3 students. You can see a picture. We've had students here in the past couple summers, and it's been fantastic, great experience for them. So if you happen to have a project during the summer, you will likely get an REU student to help you with the project and help with broader impact. And then we just want to continue, one of our main objectives is to continue to support researchers like yourself to be able to make, develop proposals to use at the site and extend the incredible research that's being done by all of you guys. So this is just another graphic that's showing a lot of the partners that we have. So some of the activities that we do to support all of these stakeholders, we have facility tours, similar to what you went on yesterday, but for the general public, for professional societies that want to have their chapter meetings, for K-12 students, for et cetera. We'll have some open houses coming up. We also have these training workshops, like I said, industry, academia joint workshops, as well as these researcher workshops. We have webinars. The webinar is going to start next quarter, and it's really just to highlight and showcase some of the great research that's happening not only on our facility, but in earthquake engineering in general. And then, again, research programs that target either K-12 or high school students. So you can tap into some of these programs and say that we will, if I will support a student through the Enlace program, which is K-12 and undergraduate students doing research over the summer. Or the IDEA Scholars, I'll do webinars for them or something like that. So these are things that we're working on revamping our Engelberg Center website, and we will include a lot of information about these programs that you can tap into. And then, of course, other outreach events. I'll show you a picture of a great one that we've done in the past, and then broader dissemination. So there is this bottom one, curriculum development, and I'll show you something that's been done in the past. I'm not saying that we actually develop curriculum based on the research you do, but we're here to support if you want to develop curriculum to bring into the classroom. So, you're doing all this incredible research. How do we create educational videos or something to bring into or even modules to tie into the research that you're doing? So that would obviously require a little bit extra funding to develop curriculum and to write the curriculum, but it's just an area that we will help support and foster in the future. So some proposal ideas. footage from the construction and the experimentation that you do, make very powerful videos for undergraduate and graduate courses. So, you know, I can show you an example of some that we've done in the past. I don't know if this is going to show. Hold on. Sorry about that. What? Anyone want Starbucks? So this is just an example of one we made many years ago. You can't hear it, can you? It's okay, we can move on. Yeah. And then it's gone. Where did it go? What did you do? I need this other screen. I had another window up there. It's going on in the background. Okay, we'll just ignore the sound in the background and we'll move on. So what we did is we developed a script. We worked with, we put together PowerPoint. We incorporated video footage to talk about the key aspects of this 5-story building test that occurred, and then developed some training modules, like 5 or 6 of them, that we could incorporate into the classroom. Where's the browser? Is that it right there?
Yeah.
Here we go. I'm gonna close it. All right. Cool. Okay. So, you good? All right. So, other things are professional videos. So we have UCTV. We have other services here that can develop high-quality videos. I'll make these slides available and make sure that the PDF is linkable so you can take a look at the different videos. But they're professionally done. They do cost money, so it's something that you can incorporate into the budget of your grant. But they're fantastic, more public outreach type of things as well, rather than sort of educational videos. And so we have a bunch of different resources here on campus to help support that. And then the last thing is we do some outreach events. We can't do this when the table has a 10-story building on it or anything else, but these are amazing outreach events that you can consider, maybe depending on the timeline, to be able to do before or after you're on the table, as long as it works for our schedule, so you have to talk to Kurosh. This was an outreach event. This is called Seismic Outreach. We do this with 4th through 6th graders. Typically, we'll go to the school, give them a presentation about earthquake engineering. We do them connects kits. They design things. We have some curriculum the teachers go through that we teach them how to do. Then they end up coming to UCSD, but not to the shake table. They come to our campus. They get a tour of a campus. Sometimes it's the first time they've ever been to a college campus. These students don't have as many resources. And then they participate in a connects competition. For this one, instead of doing all that, we actually brought them to the shake table. This is before we had anything on it. And we put, this was several underserved elementary schools, and we put all their structures on the shake table. If there's a theme that they're trying to design a structure to meet certain cost limitations and square footage limitations and try to optimize your design. And so this is just a video because it's so amazing. I think there were 100-something students here today at this day. We had 2 days of this. They were so enthusiastic. Just a day like this is enough to get them to be excited about possibly doing STEM. It doesn't have to be earthquake engineering. So, I mean, we love this. We don't get the opportunity to do this very often, but it's something that, you know, we try to fit in between things. So I just wanted to end it with that. Again, this was not meant to be a big presentation, but just to talk about, get you thinking if you're putting a proposal together with the different ideas that you can put together for your proposal. And then you can reach out to me and I can share with you all the different programs and we can kind of strategize on what might work for you depending on the time frame of your testing and things like that. So that's all I have. Any questions before I head out? I actually have to head out to the outreach event down in Southeast San Diego. So, but you can get my email through the site, and I'd be happy to talk to any of you about this. Thank you. I'll let you guys deal with the PC. Mac user, I can't use it.
I'm ready to use your own. Yep. So our next group of speakers are those working on the Tallwood project. So Shilling Tay from Colorado School of Mines is here. Oh, they got your thumb. Valerie numbers. You can record on your PowerPoint as well.
Actually, you know what? I just looking your Zoom.
Yeah, that's perfect. Or you could just make a Zoom and record it on just
Oh, okay. Okay, great. Thank you. It's a player at the privilege to come and talk with this group. Yeah, I think you've seen the real thing. So, is there any questions? No, I'm actually going to tell you the background story and my experience working with the wonderful crew of the UCSD site. Do some shameless promotion for them because it's really a pleasure to work with the site. I've done multiple projects here. So I want to give you some background about our NHERI project. So it's a funded project. It's actually 6 university collaboration, but one of the universities, Lehigh University, they finished their part at their lab a couple of years ago. So now it's mainly a full university, 5 universities, focusing on the forward testing that you saw yesterday. The great background is really suddenly it's like a child suddenly got some new toy because we used to work with steel and concrete and do really high with them, but suddenly this mass timber thing came along and you find out you can build the big buildings. So we're really excited, and then people have had a history of constructing wood buildings in high seismic regions, and we have done significant research on other wood systems such as live frame wood and push it to the height limit that's allowed by the code. And you see the third one, that is the test we did about 13 years ago in Japan. That's the tallest light frame wood building you can ever build, 6-story. Then now we're doing the mass timber because we believe that wood is first sustainable, secondly it is light, and then easy to work with. The vision of this project when we started to propose to National Science Foundation, of course, we didn't just go say, hey, we just want to test a big tall building. I think for a proposal to NSF, you need to go a little bit deeper to look at what is actually going to drive, say, the design of this type of structures moving forward for the next 20 to 50 years. The point that the angle we go for when we write the proposal was the resilience-based design, because as you know, now we have the prescriptive design, which is based on image state collapse prevention. The next level, in fact, the timber building, when we did the Japan test, it was displacement-based design, where you look at the interest rate drift and then you try to control damage. Then this one's one step further. We're always trying. It's not like you're going to get there with one research project, but we will start to see if we can do that on this project, which will focus on downtime. And at the same time, we also believe with the mass timber being a new construction type, there will be enough interest through the industry that they will want to try new things. So you got this one chance to actually do things right at first, instead of trying to put patches later on after a great earthquake. We think it's a great opportunity to kind of propose this resilient type of design idea with the industry, and then do some tech transfer. For example, right now, if you look at the SE7, there's no mass timber-based lateral system. There's one now proposed just get into the code like last cycle by Professor John Mandolin, but that's a platform-style panelized shear wall. It is very high performance, but you still get damage. So we're gonna try to do this with the rocking wall you see yesterday. So there's a great amount of tech transfer into this. In fact, at the same time, I'm actually leveraging another research funding from U.S. Forest Service to develop a prescriptive design provision so that the designer can design mass timber rocking walls using equivalent lateral force procedure or modal response special procedure. Those procedures are allowed by the code. So there's a two-pronged approach to look at this thing. Then finally, I think one last part is the outreach component, where we need to educate people about resiliency. We need to educate people about mass timber and whole mass timber. In fact, we need to show through the help of UCSD NHERI site that people what you can dream of. A tall building like you saw yesterday, built with wood, can survive design level earthquakes, 10, 20 of them, without needing structural repair. When you get to MCE, maybe you need to double check and retighten the bolts a little bit, but it is totally repaired. We want the world to see that, whether you're in civil engineering or not. The project we did funding in 2016, then we start working with it is very important you work with, if you're going to try to pull something off like that, you need industry funding. I mean, I'll tell you, like a big test like that, it costs a lot of money. I'm going to show you later. And then purely NSF funding is not enough. NSF take care of a lot of, provide the platform to make this happen, but you need industry to pitch in. So the way to do it is not to go to industry at the third year of your project, but actually involve them in the proposal writing process. So we look at what will actually sell for industry, because if your final product don't sell, they don't have interest. We kind of narrowed in on this open floor plan with glulam or mass timber beams and columns, and a very confined, isolated lateral system, easy to install, sort of. Then we did some small habitator testing, including a full-scale 2-story mock-up structure. Myself and Andre Bobosa was going to talk later. Then we move on to the 10-story. In the middle, we got hit by the COVID. We got hit by, not hit by, but yeah, we're blessed with the shiftable upgrade. There's some delay, but now we can test in 3D or 6D now. So the building, you've been there yesterday, so you have two type of rocking walls. There are two type of mass timber system, but design-wise, you know, it's the same design methodology. Then you have, you know, about 5 different floor systems. But with the floor plan this small, we don't expect too much difference. But still, we will put sensors on each floor and look at the vertical vibration, especially to look at their different characteristics. Yeah, this one is the most important slides. I won't take pictures, but anyway, this is made available to you. This kind of give you a taste of what's the proportion of the resources going into it. For a project like this, just this project, you look at the material, they are like half of what you will pay. Then there's a tremendous amount of time of engineering. It is not just me and my graduate student or my co-PS graduate student. Actually, design companies or collaborators that you see here, they actually have dedicated staff put in and then working with our students, and then of course that's all in kind, but if you really count your time, it's a big chunk of it. Then the big chunk is construction. Yeah, I saw the UCSD they charged me too much, but yeah, look at it, just small piece of pie, really not that much, you know. But fortunately, we got like almost 2/3, like three-fourths of those donated, right? For construction, you do need to pay. I think Snorri is a great company. They help us a lot. They probably like you know, 200 or 300K into this, but they still have to have real cost. You just need to be aware of that. Without those partners, yeah, it could never happen. Okay. Then I just show you some like quick videos. Cause you see the end product. You don't know how it started. We started in May. We start doing foundation. Then the members you see now in the building, they get shipped, wrapped by Smerton and Timberland. They shipped outside. It's like IKEA furniture. They pre-install everything. Then Simpson Strong sending all the hardware. Then stairs by construction specialty. Then we work with the site to first expand the table. I mean, you don't see it now, but when we first get it, and then we did how do I do that? Oh, here. We did the shift the tuning before you start construction. This is generally code up. Let me see here. Yeah, I think corrosion and optical we worked overtime to get those tuning down before contact. That's yeah. So the shiftable looks great, but yeah, sorry to be a like shaky cameraman. And then we start building first with that, and then with this. Then the first segment wall, the first segment, the second segment. Then the last segment. So 3 segments of walls. Certain, in fact, if the wall is really very challenging, if you just have them do the strong the gravity system, they can do 2 floors in 1 week. But the wall takes a long time. Here's a wonderful way. Let me talk about like how Robert helped us do drawing figures. Yeah, this is Robert's work. So it's really great for PR. In fact, we have a PR firm hired to promote the project, and they already know, and those are wonderful footages to show the world for people who haven't been there. This is actually the last panel that's on the roof, so this is like topping off. But needless to say more, I know some of you are, a little afraid of heights, so you didn't go to the top, but yeah, here's what it looks like. In fact, the beauty thing about the drone is that it's taller than the roof, that you can really get a big picture. And the one thing I want to really comment is, it is actually, I'll be lying to you. I say, oh, I had a lot of fun with this project, but I would also be lying to you to tell you that because it's very stressful. But I will also be lying to you that I didn't have fun. The fun actually is not coming from the delays, and trouble, and all that. The fun coming is actually working with people. And you can see, like my student, of course, from mine, two of my PhD students. And then the REU students, like Lily helps us to get through NHERI. I didn't spend any effort. I got wonderful help from 3 students to help us with cables. And then, of course, there's actual, you see there. The visitors, like, in fact, one of the visitors, like the middle one, is actually running e-defense right now, so there's international collaboration. Last picture, you see that's the student working on the project. In fact, there's Japanese student, there's Italian postdoc, there's people from all over the world. That's make it fun. And then the top, that's Alex, if you met him. That's the worker on site. And then the other person in white is Alicia. That's my PhD student. When you work on site, you really need to kind of you need to work together with the site, like physically. You just everybody moving, heavy metal together, and then that kind of helps build a real team. What's next? To be completed. In fact, I think we're gonna schedule to do the PT next Wednesday. Once the PT is done, structural is done. Then non-structural, Carrie gonna talk about it, my co-PI, and then she knows more than I do on that. End of January, early February, testing, so far so good. 2 phases of testing lasting for 3 months, and then we'll conduct 50 plus earthquake tests. Media day, maybe mid to late February. So acknowledgement, apparently, really appreciate NSF and NHERI program. Myself, coming from Colorado School of Mines, if you look at Colorado School of Mines, great school, little place, absolutely no structural testing capacity. So I'm actually blessed to be able to do this because of NSF and NHERI program. And again, all my collaborators in the industry. So finally, thank you, and I do self-promoting on Twitter, so if you follow me. Then you see something like some videos before the media release it, and hope some of you can come back. And then last but not the least, I encourage you to write proposals to test at UCSD, simply because it's a nice place. Me and my kids were in SeaWorld this summer. Because frankly, life, right? It's not like you do all research proposal writing. They're live. I mean, we took off like a weekend, we go, and San Diego was a nice place. Yeah, right now it's, but the summer is really nice. Okay, Gary?
Thanks, Ling. So I am the PI for the non-structural component scope of this project. I decided to tell this kind of through the lens of what it's like to navigate the process of doing this research. And I will tell you a little bit about the scope of what we're trying to achieve. Here's our team, the actual collaborative team working on the non-structural. I'm also working with Professor Hutchinson and a number of students. Shocks in the back of the room. We have many collaborators, of course, the Tallwood team, a number of industry suppliers, Southwest Carpenters Union Training Fund, and Yankee Sheet Metal have been really key for us, and as well as the site staff. So why propose a project with non-structural component testing? Most large-scale structure tests using the NHERI UCSD facility are conducive to what I call non-structural component payloads. They're basically, it's a payload. It doesn't matter too much what the structure is. It's a vehicle for delivering demands to non-structural components. And it's a great vehicle because they tend to be full-scale or large-scale multi-story buildings. If you look, so much of the structural work we have done in the past with reduced scale structures aren't very conducive to doing non-structural component payloads. The structure that we have, this tall wood frame structure, provides realistic structural framing and floor systems that can accommodate more realistic installations. And there is a need. I believe this is one of the most understudied areas in earthquake engineering. What we know about non-structural component performance is kind of at its infancy compared to the structural. We need to know more about, understand the performance of standard details. We all know, or hopefully we've heard, that non-structural component damage tends to dominate losses in moderate to large level earthquakes in areas with modern engineering, like the US for the most part. We can also work on development and validation of improved details, such as drift compatibility or component isolation concepts, and that's really what we're trying to do in our project. And I do believe NSF NIST is the natural mechanism to fund this kind of work. I haven't, thought of or come across and very many other sources that I would go to besides industry. If you think of any, let me know. So yeah, I said this already. Large building structures are the perfect vehicle to deliver demands. Alternatively, the new NHERI at UCSD testbed frame, which I think we have a presentation on this by Professor Mosqueda following ours, could be utilized as well, potentially. Okay, so how to proceed? I absolutely think, and it's a funding issue, but it's also an intellectual merit issue. You have to develop partnerships with industry. They have the expertise and the knowledge of the trade. You may have a great idea. They may look at it and go, we would never build this. We could never accept this. So how to make your research marketable to its audience. Then once you have the partnerships with industry, material donations. And I found this is the easiest part. Most partners are willing to donate their materials. Just the mechanisms they have for doing that. Getting them to put up real cash is a little bit harder. But they're willing to provide material donations. They're generally willing to provide design detailing support. These last two pieces are a little bit harder, but I think they're worth pursuing as well. You will likely need to hire subcontractors to do the installations, rely on site staff for other assistance, like receiving deliveries and placing materials. And you can expect the total scope is likely well outside the acceptable budget of a typical NSF project. As Shiling mentioned, I was part of the original team on this project, and I got, a small piece of a pie that went 6 different ways. And I really think that I would have been, or you would be better off if a project is funded separately with its own scope and have kind of a bigger budget to work with from the beginning. So, okay, so to tell you about our scope, the scope of non-structural component testing on this project, we have 4 different exterior wall subassemblies detailed for drift compatibility, 3 stories of interior walls, including conventional and shaft wall intersections, and I'll talk a little bit more about that. These are getting built right now. And a 10-story stair tower with drift-compatible connections of the stringer to the landing. A little bit of background info about non-structural walls, what we know so far. There's been a lot of testing on interior walls already, not to my knowledge as much on the exterior walls. About interior walls, we know they are easily damaged. So the standard detailing for a cold form steel frame interior wall, you have a top track, you have a bottom track, studs, everything is connected together, fully fixed, and under drift demands, has to go along with that motion, and it starts to get damaged really quickly. So another detail that can address that is a slip track connection. It's basically a horizontal joint at the top of the wall. The basic detailing is you don't attach the studs to the top track, and the slip occurs between the two. And that works great until you have intersecting walls, and then hopefully you can see here what happens at the intersection. The out-of-plane movement of the intersecting walls interferes with the in-plane slip of the in-plane wall. So I'm going to go directly into what we're doing. We really got excited about exterior walls because I think this is where, if you're going to focus energy on making good, robust details, the envelope is so important in preserving the robustness of the envelope. So we have 4 different 3-story, well, one of them curtain walls a 2-story, but 4 different sub-assemblies, one on each corner of the building. And they are, 3 of them are cold form steel frame. One is infill or platform framed floor to floor, very similar to the interior walls. The second is a bypass frame that's hung on the outside. And the third is like a bypass frame but detailed a little differently, and I'll explain that one. And then a curtain wall. We saw our beautiful curtain wall with the bright orange yesterday. And I just acknowledge all the material suppliers that made all this happen. Materials were 100% donated, other than, you know, little bits and trips to the store here and there on things we messed up on. Okay, so the first one, the platform framed it uses slip track connections. We're looking at a couple of different slip track details that we think are a little bit more robust. The first one is a nested. You've got 2 tracks at the top, an outer track and an inner track, so the slip occurs between those 2 tracks. That inner track connected to the studs helps to hold the wall together a little bit better. And then over here on the right, this is Semco's specialty product. As far as I know, it's never been tested in this way. It has horizontal slots at the top of the track. So what we're going for here is to have the slip occur between the floor diaphragm and the top of the track. And of course, I like this graphic. It illustrates what happens at the corner. To address that incompatibility, we have an expansion joint from Construction Specialties that's getting installed in that corner. And if you were there yesterday, you might have noticed in some of these walls and the gaps in the corners, which are set to accommodate those expansion joints which haven't been installed yet. The second one, this one's the most interesting, the bypass frame, and it has horizontal drift clips. So there is a unistrut attached to the edge of the floor diaphragm, and then this clip sits in it, and it's designed to slide. And so you're going to get all along this whole 3-story continuous subassembly the slip of the wall relative to the floor diaphragms. Because basically, this should stay, the whole wall of subassembly should stay upright. So you've got a huge incompatibility at the corner here. This is being accommodated by a 12-inch joint over the corner. And it's Construction Specialties. They've got this door-type joint. They say it can accommodate that motion in both directions. We're really interested to see how that one works. And then the final one, cold form steel, is spandrel units and ribbon windows. So in this case, the spandrel units are attached directly to the floor slabs, and now with a fixed clip rather than a sliding clip. So they shouldn't move. There's a slip joint, same type of detailing, at the top of the window. And therefore, the drift has to be accommodated entirely over the window region. And so we actually have this graphic doesn't look quite right, but we have 2 floors that are going to have windows all wrap around those corners. And it's interesting, the manufacturers know they can accommodate some drift, or this is probably the most vulnerable part of our test setup. We have a joint at one corner, 1 story, to, again, try to address that incompatibility. The curtain walls accommodate drift by racking, so basically they're composed of aluminum, or in this case steel mullions, with large glass panels set in between. The steel framing just racks. The glass is designed to rotate within the frame. And this is well known, this is part of the industry for a long time. But most of the testing they do is unidirectional racking tests, not a lot about what happens in the corner and so on. So this is really a validation that the system performs the way it is designed and intended. We have 3 floors of interior walls. Again, the focus is on the detailing of the joints. I put this one up for an example. We have a shaft wall around the stair system. You may have noticed that when you were walking through yesterday. Framing into conventional interior walls, and we're trying a few different joints. This is a fire barrier joint that's just basically very flexible, but still designed to be compatible with the standards for shaft walls. And then the same type of joints that we're using on the exterior being used here. So the stairs also very interesting component of the test. In like ASC 7 2016 introduced the new requirements for non-structural stairs in terms of saying you have to accommodate the demands without collapse, and there's some ideas for how to do that. Nothing's been very well tested. Our partner, Construction Specialties, again got really interested in solving this problem, and they did some research at UNR to develop drift-compatible connections. Tried several different options, fixed and free sliding. They tried some slotted options, and this is what a lot of people in the industry are currently using. And then they developed their own sliding hanger connection. I'm gonna skip ahead. I think this is the best image of how that connection works. This is showing like this steel extenders are attached back to the mid-landing, and then this unit here is attached back to the stair, and you can see this rotating hanger system can actually accommodate longitudinal movement through flexing of that hanger, and then transverse movement, this pin slides along those plates. So this is their concept. They wanted to use a lot of it. But we convinced them to try some of the other more standard details on the other floors. So we have basically 4 stories of drift-compatible connection, 2 stories of slotted connections, 2 stories of fixed-free connections. The other thing, I'm going to jump back a slide here. They have a modular stair system unit. It comes entirely prefabricated, consists of channel band framing around the top. It's supported by gravity columns, so it's self-supporting, and then the stair stringers, and they can incorporate their drift-ready connection. I think our contractor loved this because the majority of these stairs came prefabricated, and they could just crane them into place, and it took almost no time at all. And then we decided to do 2 stories of traditional construction on the top. And they were like, oh man, it's going to take us so long to put together those stairs. So, okay, so that's the scope of what we're trying to do. Like kind of a holistic, let's try to design this stuff to be drift compatible, better performance, and validate that it works. It's at a very basic level, that's what we're trying to do. Okay, so back to navigating this whole process. So I'm going to look back, maybe even 5 years before this proposal was in development. We was working on developing some partnerships for non-structural testing and other proposals going on, and working on recruiting partners. So we had a couple of workshops at UCSD. After this project was funded, I attended an AIA convention. I was looking around, saying we couldn't test this building, looking for partners. I even made some cold calls to people that I found on the web or got references to. But what really caught this whole process going was starting industry working groups. I started one for stairs and one for non-structural walls, cold form. I didn't have a lot of luck with the curtain wall industry, but the cold form steel industry was, through Tara's connections, was interested, and so we got this going. And we met every other week. We started developing concepts. We started developing plans, and no one was committing anything up front. But gradually, one by one, these material suppliers started to say, yeah, we convinced our management to donate the materials. And it was a scary process. It's like right in the beginning of COVID, who's gonna commit to donate anything now? But they gradually did, one by one. And then so I'd say some industry partners did the design and details for their systems. The stairs partner, Construction Specialties, detailed the stairs. The curtain wall supplier, Allegiant, they detailed that. But the main cold form steel subassemblies, basically students did the details with guidance and feedback from the industry partners as we moved along. Fundraising. So, that original budget I had in that NSF project was gone a few years ago. How in the world? I needed some cash to be able to do this. can't do everything with material donations. We asked industry collaborators for cash donations. This did not end up being a big source for us. Probably setting that expectation up front would have been a better idea. I didn't do that because I was so scared they were going to participate at all. In hindsight, it maybe should have been a little bit more upfront about that. This is what we're expecting. We approached some other companies, and we did get donations from CSI and Exponent. I was awarded a couple of additional grants from the wood industry and with help from Hay, and it was basically about selling, hey, these add-ons to this project are going to make it better. They're going to make the wood industry look good, and so that was convincing. And we approached NSF for supplements several times. In fact, I just went back to them and I need some more cash to finish on this construction, and it was successful. So experiences identifying and hiring contractors to build. For the cold form steel framing and sheathing, we partnered with the local Southwest Carpenter. It's great, right? We were able to do that. They'd been on site before. It took a while to establish the new current contacts, probably over a year, but we eventually did. And that was a huge help and a huge cost savings to us. We actually explored a similar partnership for the curtain wall installation, but that didn't end up coming through. For the curtain wall, okay, I knew I had to hire a contractor to do this. I reached out to multiple local contractors. I eventually got 5 quotes and selected one. It was a long process, but I had enough time. For the exterior skin panels and joints, so first of all, I was trying to find someone to just donate the materials. And I started with a contact from the AIA convention. He referred me to 3 local sheet metal contractors. And I cold called each of them, and I got lucky enough to run across Bill Taylor from MP Sheet Metal, and he was interested. He's interested in the seismic stuff, and so over time, he agreed. He worked with all of his suppliers, get the materials donated, and then the agreement was that we would pay for the installations. So they donated materials and design work. We're paying for the installations. And then interior walls. So I kind of explain a little bit about this on the next slide, but I needed a contractor on short notice. And who am I going to ask? And everyone said, oh man, it's going to be so hard to get someone now. Everyone's so busy, and I had a month lead time. I just sat down one day. I started looking through the construction blue book, and I called about 20 local contractors. Only one came through, but one was enough. So that was, I felt someone's watching over me here. All contractors and volunteer workers were required to provide certificates of insurance to UCSD. If you have a volunteer labor, that's all that's needed. They need to provide insurance, no other contract. UNR is probably one of the hardest institutions to work with to get contracts through. They don't understand what you're doing. But they required also these contractors, a little typo on my slide here, to provide insurance certificates as well. And that wasn't a fun process either, but finally we've got them all through. Other challenges, this is interesting. Every contractor underestimated the time they needed to install their components. Every single one of them. Why did this happen? There's 2 major challenges, I think. First of all, there's the tendency for look at your details, your highly specialized, new, innovative details, and they underestimate the time and efforts it's going to take. They think it's standard, and they show up and they go, oh wow, this is really different. How do we do this? I think every single contractor is making that mistake. So schedules kept slipping. And the second thing is just the tiny footprint on working on site. So this created a real problem for us when working with the Carpenters Union, who had locked in their class schedules well in advance. And what do we do? It's not the preferred approach. The site does not prefer this, but we negotiated for multiple trades to work in parallel to keep things moving. We made it work. We took as much advantage of the Carpenters Union during the time frame we had. It was a little difficult for them because we couldn't give them continuous access, and they weren't very happy about that, but they still helped out as much as they could. I felt like a construction manager kind of trying to manage all this work. Totally unqualified, but placing materials for installation during building erection was not possible. Oh my gosh, I'm worried about this for a month. How are we gonna get this gyp board up into these upper stories? Normally they would be placed as the floors go up, and there was just no room to do that. So we actually placing gyp board this morning. I got dust on my pants from coming in. But I mean, finally my nightmares are starting to appease here because they're getting it done, forking the materials, and the contractors have to haul it up the stairs. And what else? The site staff do not appreciate surprise material deliveries. For some reason, this happened a lot during our project, and I don't know why. Because like toward the end, we were like, okay, you really got to let us know, and it still happened. I don't know why. Yeah, one other thing I thought I might comment on, probably taking up too much time, but how do you pay for all this travel as well? So Ling rented a house, 4-bedroom house, for a year, and Dr. John Vandelant paid for some furniture, and he's distributing out. I paid for a few months, he pays for a few months, etc., etc. There's about 8 of us living in that house right now, sharing bedrooms with our students. It's fun. It's a fun experience, but you do what you need to do, right? Because you can't afford to stay in hotels every single night for a year. So, okay, so here's some pictures of watching the fun part, watching these specimens go up, the curtain wall framing. That was really neat to watch. You can see they're handling some of the glass, and they use this this device to place some of the heavier sheets of glass. It's the finished product. During the cold form steel, it was really interesting watching the framing go up because you can really see some of these details. This one, I think is you can see those slotted tracks. You can see the double slip track at the top of that one. This shows those clips that get attached to the edge of the slab. And once you cover it up with sheeting, you can't see as well what's going on. So I liked being there and seeing the framing go up. Here's kind of more where we are now. Finished, we're just waiting for this one has waterproofing on, the other two need to get waterproofing, and then flashing and window installation, and then finally the metal panel on the joint. That contractor's really getting going next week. Here's one of the stair towers being framed in and placed. Stairs, yeah, a couple of different visions there. So, conclusion. I don't have any conclusions. The end of this story is not written yet. My own personal vision here. What can I say? The most challenging endeavors are also the most rewarding. After 10 or so years ago, I finished up the Nice Tips project in Japan, and oh man, this is one of the hardest things I've ever done. And I thought, I'm never doing anything like that again. And years later, I looked back and said, oh wow, that was such an amazing experience, produced such amazing results. Well, this one is twice as hard. So I think it will be twice as rewarding in a few years down the road. But we're in the weeds here. It's pretty challenging. Okay. Research project. Here's all here's all the collaborative NSF grants that help us do this project, and USDA's direct grants from USDA, and a number of material donation. And Ling's slide was pretty comprehensive on that. Okay. All right. Very good. Andre.
Oh yeah. Why don't you just do that because I'm recording.
everybody, and I'm really happy to be here as well. It's always good to come back to UCSD and see some familiar faces and some new faces as well. Before I start, just a show of hands, who identifies themselves as a structural engineer? How about a geotech engineer? So hang in with us, okay? Because it's been a lot of structural engineering information that we're throwing at you, and there's going to be a little bit more. But I'll try to make it informative as well, you know, on top of what Ling and NHERI already did. Okay, so you know, thinking with Ling and collaborating with Ling, this gives an idea of what now I'm going to talk about, which is a 6-story project that's going to follow the 10-story project that is on the shake table. But if you look at color coding, if you look at number 1 up there, you see the NSF Tallwood project, so Ling project in 2017 in an earthquake engineering conference in Chile. After talking with Joel over lunch, and you know, Ling talked about people and friends. A lot of our collaborations have been around dinner and around beer. Okay, and that's how we developed a lot of the work that we're doing together. But early 2017, Ling already had a funded project. We had started writing a proposal. We didn't have funding yet from USDA ARS there on that top left box, but we had started the work that Kerry was mentioning, those partnerships. We had already started working with industry, talking about, we wanted to do some testing. At the time, it was testing at a lab at OSU. We had talked about what we wanted to test, and there was interest from the industry. But that conversation, early 2017, in a conference in Chile, we said, okay, what if there was an opportunity at the shake table, there was a gap in terms of no projects on the shake table early 2017, and said, can we pull this off? Can we pull off the initial project? Ling was to test the 10-story, but there was additional information that would be useful for the design. Can we pull it off? And between January, you know, Santiago, Chile, January 2017, and May 2017, in a crazy timeline, I wrote the USDA proposal that provided a little bit of funding. Ling did a lot of work getting collaborators and companies, industry also in, and had the NSF funding that allowed us to use the shake table. But by May 2017, we were on the shake table. So we wrote proposals, we worked with industry, doing design, and we ordered material. Material was delivered. May 2017 is when we started this 2-story project, which was really great to learn a lot of things of working with the site as well, and also working with industry and telling them that this can be possible for a 10-story and as a first phase. We continued working with funding from USDA, and at the same time, there was in Oregon, there's been a lot of push by senators, by local governments to push mass timber because it's one of the main products that Oregon produces, and there's lots of jobs, and is also sustainable. So it's probably, mass timber is the only topic in Oregon and the Pacific Northwest that does not have political boundaries, right? Everybody's interested, be it because it produces jobs, right, and you're in rural Oregon, be it because it is a sustainable green product. So you have both camps promoting, and it's, you know, it's very easy for a politician to put their hat on mass timber because everybody was supporting. So for Oregon, the Pacific Northwest, and here on the number 2, we got some funding and went into industry to help us do a new lab. We have a new lab which allows us to mainly do work around timber. We can also test other structures, but we have another lab at OSU where we do steel and concrete research. And we wanted to have a signature test, which is a 3-story test, where we're testing different lateral resisting systems, and I'll show some of those results here today. All along this, we kept talking with NSF saying that this was going on, and you know, Joy was informed about efforts that we were doing around this 3-story. And there was the 10-story project, the one in blue, who was leading and doing an amazing job, and still keep going because we're almost there in terms of testing. But that's the team that he presented, 6 universities and 4 main teams, folks now focusing on, we, from around 2019, 2017, we were collaborating, so us at Oregon State University were collaborating, but we didn't have any funding and we're not part of the 10-story project, right? We're just good collaborators, and Link is an amazing collaborator. Around, and I'll show more about that later, but around 2019, we started thinking, okay, there's all these opportunities and gaps in terms of funding, and we started thinking, what if we did something around the 6-story test? Because there was a 2-story, there was a 10-story, there was also a market analysis done by Woodworks, which is an agency that's mainly funded by U.S. Forest Service and USDA, but also some industry funds. And they had come up with a conclusion that the sweet spot right now, in terms of where these mass timber projects really pay off, around the 8-story, 6 to 8-story is where they really pay off. And so 10-story covered the 8-story and taller. The 2-story is on the lower end. We needed something in between to also inform designers. And as Ling started looking at budgets of what would it take to demo, because once we do a shake table test, we need to also take out the structure from the shake table. We started thinking, okay, what if we do try to get additional funding to support the demolition? And immediately, if you demo 4 stories, there you are. You have a 6-story building that you can work with, and then that in itself, just because we wanted to test the 6-story test, would not really cut it for NSF. So what we created was as a proposal around this idea of working with functionality-based design and multi-objective optimization. Okay, that is integrated in what we call a converging design methodology. So you'll hear more and more in the future about converging design methodology, where we're addressing resiliency, sustainability, and allows to integrate innovation, specifically for us focusing on seismic lateral force resistant systems. If you haven't written, but if you're writing, or if you have written NSF proposals, you always have to really be clear about what is your intellectual merit, right? And these were our 3 main intellectual merits. We wanted to define functional recovery and sustainability metrics that could be used in design. We want to quantify their uncertainty, and we want to be able to integrate them into design innovation. We want to create and implement this multi-objective optimization in a convergent design methodology, and then develop optimized seismic lateral force resistant systems. The way we organize this in our work plan, on the left, you have to turn your head a little bit. The gray box is the 10-story NSF Tallwood project, which is not just a 10-story test. There's also a lot of other scientific merit around it. But for us, we had task 1, which is working with not just us as researchers defining what we think is best for design, but working with experts, working with industry, working with a panel that I'll show you next, to make sure that whatever we want to propose is consensus-based, and we've heard different sides of the story for it. So developing a series of workshops and developing archetype buildings as well. Task 2 is prototyping solutions for convergent design. Task 3 is that methodology implementation, where we'll be looking at optimization, and we'll also be looking at integrating all of this into a design tool, and then validating our methodology. The ones in green are the ones I'll focus on here today. In terms of the testing, I'll also mention a little bit just about task 1 over there. Outreach, getting things out in codes if possible. That's task 5 there in terms of dissemination and outreach. For the 6-story project and for the convergent design methodology, this is a team. So up there in front, until recently was all OSU, myself, Ari, Singha, and then Mark Simpson. She recently moved to Stanford. And then at Penn State, he's an expert in optimization, Dr. Nate Brown, and then Sean Vanderlyn as well. This is thinking. We have be possible, again, with our students. So top four and the one on the bottom left here, they are funded, or partly funded through this project. And then we have other students and a postdoc helping us that are not funded through this project, but also doing work for the project. Collaborators, again, none of this would be possible without Link, so Link is a collaborator. We have up there 2 industry collaborators that do a lot of design with us. And then, and check our designs, serve as our peer reviewers. And then on the right, there are architects as well, so making sure that what we're proposing structurally is within the context of what would actually be used by architects. And then at the bottom, we have a series of, so a group that was put together during the proposal stage, many calls, like Kerry was mentioning, of building those partnerships, but on around design optimization and construction, so Swinnerton, Lever Architecture, and SOM. SOM is from the architects, they do architectural work and also structural work, but focusing on the architectural work. And then we have both on the regulatory folks, so Amit Kumar with the City of Portland, NIST and AWC, American Wood Council, they're as well overseeing, and we regularly tell them what we're doing and get their feedback as well. We have the industry. From there's been this tension between wood and steel and concrete industry, and that's not our play. Our play, even from the beginning, was to bring folks. At the time, Glenn Bell was with the Panka Foundation, but mainly representing there the concrete industry. And then we had Woodworks, Simpsons on Tie with a lot of steel, and some manufacturers as well. And then, in terms of the outreach, but also to integrate whatever other folks are doing internationally, we have international collaborators there as well. So, this task 1 is consensus building, and it's making sure that we are integrating in design whatever it makes most sense. So we've run already a series of workshops. The one on top was a workshop on functional recovery, working with NIST. Yamax Natar gave a presentation. Abby Lyle, that ran recently an ATC project on functional recovery, was also a presenter. And then we had our team that I showed you there was all present, either in person or in Zoom. We've been still managing this hybrid mode after COVID until recently. So we actually had 3 groups that were in workshops, so 3 groups working in the room, and we had 1 group that was working online. You can see that on the top right there. And at the end, all of us working on Google Docs, reporting back the workshop summaries, and then discussing the results. We've done one in Madison, Wisconsin, in the First Products Lab on sustainability. And there we are reaching out, and we have been reaching out to ASE, SEI, SE 2050, so with the Sustainability Committee, because they are trying to bring more and more sustainability into structural design as well. And so just making sure that we can bring that, and how do we bring that into design. We've participated within one, the ATC Functional Recovery Workshop, and then we're putting out a sustainability survey based on workshop number 2 over there, the sustainability workshop. And then we're going to have other rounds of functional recovery workshops and sustainability recovery workshops. So building that consensus and making sure that whatever we bring in that divergent design methodology is what folks would actually be using, even if not immediately here in the short term. Moving to task 2.3. There's a slow slides coming up. Computer. It's actually telling me it's restarting PowerPoint. That's okay. And then PowerPoint is restarting. We have the 3-story test. No, that's not ours. It's okay. Okay. three-story test. This is a quasi-static cyclic test. It's uniaxial. This is a 45-40 foot plan and three-story structure. We're looking at different diaphragm designs, and so that's why we also have the diaphragms, blue lamps, different connections that allow for up to 5% drift. But they were also tested in the two-story test. And then the main focus is on two lateral resisting systems. I'm going to focus on this MPT pivoting spine phase 1 that's up there. So three-story, full scale. This takes us to the limit of what we can test in terms of height in our lab, in our new lab at Oregon State University. And then the show is around that wall and the connections in that wall. This wall uses BRBs, but not in where they are. You've usually probably seen them in structures. Buckling restraint braces are usually our diagonal elements in the steel structure. Here we're using them as vertical elements. And I think he just stepped out, but you were there yesterday with Jose Restrepo. He was showing how the walls would rock, right? Rock up. So as these are going to rock up, we're going to have one BRB goes into tension, the other one goes into compression. In this particular design, we thought, okay, what if one mode of failure, one mode of damage is actual compression at the toes? What if we elevate the load, that wall that is only going to carry shear, we have to transfer the shear somewhere, so there's a shear PSPN, and then this is a pivoting spine. Spine, just because it holds the building up, just like your spine, and then, but it's a shear wall that is a pivoting spine shear wall. At the top, you have to transfer the forces from your BRB to your structure. So usually it's all in the connections that a lot of work goes into designing mass timber structures. I was just showing how this would rock, but conceptually, this is like the easiest of designs. You have to go back to basics, but it's pivoting about this point, so you have some compression over there. There's rotation. One goes into tension, the other one goes into compression. Shear is taking up the shear key. And then, just so that when the buckling restraint braces and the steel element, as it starts yielding, they would tend to grow in height. We have this rod just to hold it down as the BRBs would want to walk up, so that the wall is always connected to the structure. So this is pivoting spine. And there have been efforts, actually, an amazing researcher in Japan had done similar things for reinforced concrete structures, but we adapted some of the ideas and the concepts for this mass timber structure. It's all in the connections. We have to transfer the forces, just like we saw yesterday on the 10-story building. We have to transfer those forces from our main lateral resisting element, here a laser pointer, which is this one, to the walls. So very similar design. This is the design that goes on both sides of the force that transfers to both sides of the diaphragm. What you saw yesterday on the 10-story, because of stair openings or because the walls are at the end of the building, then it was just one-sided connection. But very similar ideas that go there into those connections. Now, can't thinking too much. I think your computer has been, it's like Ling has been overworked, his computer has been overworked. Okay. After we do our construction, and more we're using laser scanning and other tools just to make sure that we can have our as-built, right? Where are things actually there? We're also using laser scanning, and I don't have any drawings to show you, any figures to show today, but as we're doing our deformed shape, this is a quasi-static test, so we can hold the structure at a certain point, do a laser scan, and we're doing something called dynamic laser scanning, which, working with the software and changing the software of the laser scanners, you can actually, instead of doing, a point cloud, which does a series of LiDAR shooting and collects the data from LiDAR, and doing that around 360, you can just do in a line, and you can actually get around 30 to 50 hertz of data. So you can do earthquake tests and collect points along the height of the building. So we've done that validation for this test, and we're going to apply it for the 6-story test as well. And then I'm going to leave out these links here so you guys can see later. We have a code review. You can actually view your laser scan, and then the student got excited and created like a 12-minute video of the process of doing laser scanning. And so there's that link there as well that we're sharing. In terms of design, we designed it, and then we went to test it. And this is recent as about a month ago. It's a cycle test, and this is a lapse at the largest strip, so you can see the wall or the building moving. And then this one here, you can actually see the wall rocking at the base there. And so in both directions. So the gap is almost closing. That was the design target. Didn't actually touch, again, our design target. We were up to 4% drift. And we had some minimal damage in the BRBs, that what they were designed for, but no damage at all in the wood structure. And the connection works as well. Again, in terms of concept, you can see right there at the bottom, our engineering model is easily transferable to what we can see in the actual test. So it's a very clean design in terms of going back to basics there. Okay, now I gotta move past this slide. We're going to have a phase 2. This one is using UFPs, but concentrated at 1 story instead of having the UFPs, the elements distributed over the height of the building. That's set for January 12 and 13 here. And in terms of the 6th story, so this task 4.1, we're going to have 3 phases. We're going to have to deconstruct. We're going to be reusing the wall that Ling is putting in. And then swapping out the UFPs so that we learn the same system, but now at 6th story. We're going to have a phase 2 where we're going to bring in this BRB solution with post-tensioning. We have not tried yet with the post-tensioning, but finalized the design and it should work as well. And then recently, and this we're actually keep looking for gaps in funding. Simpson Strong-Tie said they were really interested in testing a new solution that they came up with, which is basically a new buckling restraint brace solution. So we're going to have a hybrid. We're going to have a steel lateral resistance system with the mass timber gravity system. And we're working on the design now. This is all pretty recent. I'm about a minute over, but let me just go over it in terms of milestones and some dates that you guys will see when we share the slides, and slides are all going to be shared. But in terms of timeline, you can see just how things take time. And for example, 2019, there was a 3-story proposal we submitted to USDA, and then we completed the 3-story designs in 2020. In October, in December 2020, we submitted the NSF proposal for the 6-story, but the ideation for the 3-story and 6-story was in 2018. Okay, so if you go between there and there, it actually took us about 2 years to really do the NSF proposal. But it's not that we were just waiting. We were continuously talking with folks, like Terry was mentioning, continuously working with Ling and team, and it was huge in terms of support there as well. In 21, we did the 6-story kickoff meeting. Our project advisory kickoff meeting was a little bit later. And then we've been doing our workshops. We're in this phase, the scary phase that Jerry was mentioning. We've been having meetings with contractors since October. We haven't gotten one to commit to any budgets. We haven't gotten one to give us a budget. But we've had a lot of conversations with them, right? They're not committing yet, like Kerry was mentioning, but they're interested in continuing the conversations. They haven't left the room, but they haven't committed to any funds yet. Not only funding, it's actually, we want to pay them, but they don't tell us how much they want us to pay. And then phase 3 ideation was in October, right? Main takeaways, timeline, we come up with Gantt charts. Don't spend too much time on that Gantt chart because it's going to be continuously adjusted, right? We are hoping to get in June, July, and we have to be out by December. And that's right now fixed, but other than that, there's continuous, lessons learned in this project. I really like this idea of 1 to 3. I was looking at numbers by Link today. It's more like 1 to 4 in terms of there's 1 unit that you get from NSF. You probably need 3 or 4 times that to actually do these types of projects. Co-production is possible and it's true. Carrie mentioned a lot all the work she's doing with her industry partners, but you have your academic collaborators, industry partners, and leveraging other projects and other tests, and just being flexible so that you do allow others to contribute as well to your project. Trust and effective collaborations and partnerships is key, right? And the idea of trust is key. If you start building these partnerships, if you do something even once, and you're, bluntly speaking, you're pissing off someone, that partnership may not last too long, right? Or people may just walk away from the project, even during the project. So trust, communication, collaboration is really key to make it work. For example, one thing that we're continuously now still looking for is we do have to take out all those panels. And so we're looking for additional partners and additional funds. So what do we do with those panels, right? So we haven't, even though we're working on the action of doing the project, we haven't yet stopped looking for other opportunities on those funds. All right, thank you.
Great, no problem. So let's take a 10-minute break. Come back here.
Structural systems, but we're to use it as a vehicle, as Kerry talked about, to test on structural components. The building is reconfigurable in the sense that you could frame it as a moment frame using the Durafuse connections, which are replaceable fuses, or you can use it in a brace frame configuration using BRBs, which again are replaceable fuses once you damage those. We're good, or? Should I start over? Yeah. So what you will need to do is to use this building is really look at what parts you need to replace, tune it to your particular properties, and get those issues. It also has, in addition to these systems, a compliant base that oh, I think it's stopped now. Robert,
Oh, it's stopped?
Oh, let me see if I can get this. Oh, there you go. Okay. It also has a compliant base with threshold tankers that allow for some flexibility at the bottom base, right? Because if you have, for example, the moment frame configuration, in order to develop a full plastic mechanism, you're going to start hinging at the bottom bases potentially, right? And so it has a compliant base to allow additional drift without that, the buggy braces, as I mentioned, and the Durafuse. So in the as-tested configuration, you can always add more weight, of course, but it's about 300 pounds total weight. 300 pounds, 300 kids. Slight difference there. And it has floors. It has steel plates for additional weight. It also has some concrete flooring in there as well. Some removable concrete flooring they could attach to the building as well. And again, so these modular diaphragms are all available for reuse of the structure, right? The modular decks and the steel plates are providing the total weight. Now, based on these are going back to your predictions and some models that have been done. These are the types of different behaviors you can get. You change the stiffness, you can change the strength depending on how you design your brace frames or your moment frame connections for the system. And all these, what I'm talking about, is in the longitudinal direction. In the lateral direction, it's typically only tested in the brace frame configuration. The building has been erected twice, one on the staging area while the kitchen table was being upgraded in 2021, and then testing was conducted in May 22. And it takes about 2 days for erection, 1.5 days for re-erection of the system. I think Michelle will talk more about kind of budgeting for that. And the erection of the staging area was really good in terms of kind of identifying some problems for faster construction of the facility. Here's a video that, please. Oh, there we go. Oh, I think I stopped it. Took too many times. But you see the brace ring configuration and the moment configuration. You can look at kind of the differences in flexibility of the two systems. This is under the Rinaldi receiving station, full scale, 3D record applied on these systems. And you can see kind of the test under the different, and look at the different dynamic properties you can get, what you're looking for, depending on what you're looking for in the system. Again, this intends to be a community resource. We're currently working on developing the, analyzing the data, of course. The test were just completed in May. We're hoping within a year of testing to have the data and available for the community. Publish it on DesignSafe along with Jupyter Notebook. The drawings, data and numerical models from the test program, make that all available. So again, this test was just completed in May, and all this is underway. How you can use this, for potential ways in which this can be used is, to test non-structural systems. It's a vehicle to apply load, as Kerry mentioned. And you could also look at, changing the structural framing system. You could, put the frame on isolation. You could add dampers instead of BRBs. There's a lot of different configurations you can play with. The idea is that you have a base structure to work with, and you don't need to worry about building or designing and spending the money on this additional structure, and hopefully reduce the cost. Now, I think Michelle's gonna finish this up on.
Yeah, so as far as for the users, future users, we just wanted to give you guys a few things to keep in mind. So, the beams and columns, base plates and all these connections are considered usable, but there's some aspects or some components that are not. And so the BRBs, the fuse plates, stretch length anchors, and the hardware, so bolts and nuts that join everything together, we consider those consumables. So that's something that you'll have to budget for in your proposal planning. And if you want more information on cost of these things, estimates, just reach out to one of us from the management team, and we can get you that information. You also, of course, have to consider the costs and schedule associated with erection and de-erection. And so I put a kind of an estimate there, something to think about as far as what those costs could potentially be. But again, contact us, we can give you more, reach out to contractors or help you to reach out to contractors to get more detailed information on those costs. And the last thing is that since we want this this resource to be reusable for future users, we don't want any damage to occur to the columns, beams, the elements that we consider non-consumable. And so if you're going to make major changes to the configuration of the structure, using different load histories outside of what's already been tested and validated, then we're going to ask you to do some detailed nonlinear analysis to demonstrate that demand capacity ratios aren't exceeded, so that we don't end up with any unintended damage to columns, beams, things that would be very expensive to replace. Of course, hopefully in the coming future, we'll have validated nonlinear analysis tools that we can give you to get started on that nonlinear analysis, but we will require you to do that and demonstrate to the team that everything is going to be okay for your testing. So with that, any questions? We'll wait till the end of the session. Yeah. Thank you.
Next, we have a presentation on city centers. So, Adam, I think your presentation is here now.
Hi, good morning everyone. My name is Adam Charnutze. I'm a research engineer at Stanford University, and I will present with NHERI, who is a postdoc with us at the SIM Center at UC Berkeley. We are going to talk about, provide a general introduction to the SIM Center, but also focus specifically on how it would be useful for early career faculty like you. So we will show a couple of examples. In the end, Sandri will show 3 examples where this was used to help and aid experimental research, or how we could imagine it would help such research. And should just to give you some thoughts, and hopefully it will spark some questions that we are very happy to answer in the end. Before we start, I want to take a moment and do what Anand did yesterday about design safe. And I would like to ask you, who knows about the SIM Center already? Oh wow, that's so easy. Okay, how many of you have participated in a webinar or some kind of a training or something with it? Okay, and then this is the most difficult one. How many of you have actually used one of our tools? Yeah, okay, that's normal. It's kind of wrong. Yeah. So what I'm after here is to encourage more of you to use our tools, not because you have to. You don't have to. This is not something NSF requires you to be successful with your proposal. But I really think that these tools can help you already writing a good proposal. So it will help you with the broader impact part. It will help you with the intellectual merit part. And then once you are successful with your proposal, I think it will help you deliver what you promised. But let's see. We will get there. So first, I want to start with the acknowledgements to show you that this is not a 2-person project. Sandri and I are just here to represent SIM Center. We have 35 people involved in this project. It's a large effort. You have faculty, and you have postdocs, and we also have a lot of students who are helping, who are not even listed here. So it's a large effort. We are just 2 of the many that are working towards this. And we are part of a bigger family here. You see a presentation yesterday, you saw it from Design Safe. You are seeing a couple of things from NHERI, right? From this side, there are other experimental sites involved in NHERI. We are all working together, and we are hoping to build a community around natural hazards engineering. So it's not only about connecting earthquake engineers with hurricane and tsunami and coastal engineers, but also connecting people who are working on roughly the same things in many different places in the country, and trying to make it easier for them to share the knowledge, to share the models, and so accelerate innovation, as I like to put it. That's one of our main goals. If you look at what our mandate is in our proposal for NSF originally, the first sentence is very telling. It's to advance the nation's capability to simulate the impact of these disasters. But notice that it says to advance the capability. So it's not enough that we work on the next generation of regional disaster simulation. It's not just the tools, but it's making everybody use those tools or enable the use of those tools, even to research groups at smaller universities where they might not have the courses available, for example, to teach their students how to do these kinds of analysis. We provide webinars, we provide tool trainings, so that everybody has access to this knowledge and to the tools that are required to do these kinds of analysis. And this way you can prepare a competitive proposal with bigger universities or with other places. So really everybody can participate. That's what we are after. And that's why, besides the development of these tools, we put a lot of effort into education and training of your students or yourselves if you are interested and you have the time to spare. So how do we do this? And this is also very important. We are not trying to prepare the simulation platform, one single way to do the analysis that is the perfect workflow. We are more interested in kind of like a toolbox kind of approach, where you have your own toolbox for simulations, for workflows, and you pick the kind of tools that you need for the problem that you are looking at. And you are using only the tools you need, and hopefully you will find the right level of resolution, complexity, and fidelity with those tools. So what we did is we started from the performance-based engineering framework that was originally developed at the Peer Center at Berkeley, and took that from an individual building level and scaled it up to regional assessments. So we are thinking about doing regional simulations, but keeping in mind that in order to do those simulations, we have to have a good understanding of how individual structures and how soil behaves. So we are thinking about geotech, we are thinking about structural, we are actually thinking about other things than buildings as well. Bridges, or it could be dams, or other kinds of structures that are also part of the built environment. And at the end, as you can see from the workflow steps here, we are also thinking about recovery. There's not a lot of people here who are involved in socioeconomic work and recovery analysis, but we are also talking to those people to make sure that they can take advantage of some of the work that you guys are doing. So maybe you bring in a new way to model something in geotechnical engineering, but that can improve our understanding of the damages in a city. And that can improve the research that others are doing on recovery or on the insurance market or something like that. And it is these connections that are very difficult to establish as a young faculty. But if you're working with us, we can help to channel your models and your results and your contributions all over the community so others can take advantage of those improvements as well. So starting from this performance-based engineering, we have this conceptual workflow idea, but the important thing that I always like to emphasize is that we imagine each piece of this workflow as a puzzle piece that is interchangeable. So we have each step going from understanding the building or the building inventory all the way to recovery simulation, but you can put together different kinds of workflows to do this job, depending on what your research question is. It could be a very efficient and idealized model, or it could be a high fidelity and very expensive model for each step in the workflow, depending on what you are after. Everything we develop and everything we share is open source, and it's shared with a very permissive license, so it is even available for commercial use. If you want to do some consulting, for example, or if you want to work with someone from the industry who would be interested in your work and in your models, but they are typically used to having very limited access to academic resources because those are not available for commercial use, these are available. So every tool can be used by industry, and there are a few companies that are already interested, companies like Dagenco, for example, who are interested in these tools and are starting to use them for their own work. So let me give you an example of how this works in an earthquake context. We also work with other hazards, by the way. So there's another thing that you can do here is bring the multi-hazard aspect to your research if you are interested. If you look at different places in the country, usually every place has a dominating hazard, but there are other hazards that needs to be considered. For example, in California, besides earthquakes, there's wildfire, right? And there's flooding that doesn't receive a lot of attention, but flooding is a huge issue in many parts of California. And that's just California. If you look around the country, there are many types of hazards that could be considered, should be considered in parallel. So, staying with earthquakes, if you start from the hazard side, again, thinking about the geotechnical faults, we could use ground motion models and empirical relationships, but we also have a site response model built in. So you can characterize the soil and you can propagate the ground motions through that. And if you have other ideas on how to do it even better or even faster or a better way to model that idealized relationship, we could build that in. Everybody else down the line would benefit from a better understanding of soil amplification, for example, or soil structure interaction. Then there is the part where you describe your building or your structure. You can use archetype buildings, or you can use the models of someone else that was shared on DesignSafe maybe. As long as they are shared in a format that is compatible with our platform, it is as easy as just downloading the model and loading it into our applications, and you can run with it. So again, thinking about the geotechnical engineer, you could use some realistic structural model for your studies without having to worry about developing that structural model, because you just know that it was developed to work with our systems, and it was vetted, there's a publication behind it, you can go ahead and use it. And if I flip it, someone could use geotechnical models coming from another research, right? And then combine it with their own structural model that is developed. There are different levels of analysis that we support. We support things that don't even require finite element modeling, like a capacity spectrum kind of approach. This is usually for large-scale regional studies where you need to be running something that's efficient. Or you can use detailed finite element modeling in OpenSeas. You can also use other tools. It's not limited to OpenSeas. We have examples where we used ETABS or Perform 3D to run analysis. We have some CFD analysis that were done in Ansys Fluent. So there are commercial tools that could be available. Of course, we don't have the licenses, so you would have to have your own license. But other than that, we can connect with those and run the analysis in those programs. And once you have an understanding of how the structure behaves, you can move on and look at the damage and the consequences of the damage in the structure. Again, think about a research where you do not know much about this part, but you would be interested in seeing how it's impacted by the changes that you make earlier in the workflow. You can use the results and methods developed by others that we make available and see how the damages are affected, or see how the losses or consequences are affected by changes you make earlier. I think this is a really good opportunity, not just for collaboration, but for increasing the impact of what you are doing and showing how changing a part of the workflow can have a broader impact all around the calculations and the community. Now, what we develop at the essence is Python and C++ code. You can run it from the command line, you can run it on DesignSafe, you can run it locally, you can run it through Jupyter Notebooks. But we understand that a lot of students or novice users find that still difficult, even Jupyter Notebooks. So we also develop desktop applications with graphical user interfaces to make it very easy for someone to get started with these tools. Our experience is that most of the students even get started using the desktop applications and then they navigate to the command line eventually when they learn it. But for the initial buy-in, to get them hooked, these applications are very helpful. And what we do in these applications, the general layout is following these puzzle pieces. We have a bar here, and you just walk through each step, each puzzle piece, and a new panel is presented for each puzzle piece, and you can select which method you want to use among those that are available. So it's very convenient. If you have a student, you can teach them how to select the right method, even if they don't know much about the theory behind those methods, because it's a drop-down menu. They select one thing, they set up the parameters, and they can move on and focus on the part that is actually your research or your area. So these applications come in different flavors because we want to make sure that they serve each type of researcher or research group in the country. We go in a hierarchical fashion from basic calibration problems, and by basic I don't mean that these are simple. Calibration is not simple at all, but that's like the building block of everything else that comes on top of it. And from calibration, we go to response estimation, performance assessment, and regional simulation. So all the lower three are individual structures. The top one, the regional simulation, involves potentially millions of structures. Depending on your research area, you will probably be interested in one of these or two of these only. But you have to know that by contributing to one of these, you are also contributing to everything else. Because if you do a better response estimation method, it will help performance assessment of a single building, and that will help performance assessment of the region. So there is this interconnected nature and between our applications, and every application we have, these desktop apps, use the same backend engine. So everything is running the same scripts. It's just running the different part of the workflows to serve your needs. So to give you a quick idea of how this looks like, I will go from regional to regional simulation all the way down to calibration to show you what these applications can already do. So these are not plans, these are not some long-range visions, these are things we already have in those applications, and examples also to support you getting started. So R2D is our most complex tool. It's for regional simulation. It supports earthquake, hurricane, and tsunami hazards, and it supports buildings, and we have just rolled out lifeline support for buried pipelines. So you can look at infrastructure, you can look at buildings, you can look at both at the same time, and you can look at potentially millions of assets. This is typically not what you guys are doing, I think, but I wanted to show you the impact you can have by changing what individual buildings use for the assessment, right? Because it goes all the way to these types of analysis. Now, in order to do these types of analysis, we need to understand the damage to individual buildings. For that, we have another tool that focuses on a single building and allows you to choose from different ways to calculate the damage, to calculate the consequences of the damage. To do that, you also need to have a good idea about the response of the structure, right? In order to get the damage, usually you use some kind of drifts or floor accelerations or something like that. If you are a geotech, you would need to understand how, say, liquefaction affects the building, how much deformation or displacement you should expect. In order to do that, we recommend using our earthquake engineering tool, which is only going until the response part, but it allows you to focus on those things by looking at different hazard models, for example. For earthquakes, you can use stochastic ground motion simulation. You can select ground motions from a database like the NHERI database to match a particular hazard, to match a particular response spectrum. You can bring your own ground motions if you want. You can use physics-based ground motion simulation results. All of these are already available to make it easier for you to put together some simulations without having to worry about each piece or each part of the workflow. We also have different models available to automatically create OpenSea's models of structures for steel frames and for reinforced concrete buildings. So if you know what kind of steel frame or concrete building you would like to model, you provide the details of the building, and the OpenSea's model is created automatically. Again, you don't have to worry about how that works, it just works. And then the essence of everything is the calibration of models. And I think this is where you might find a lot of value working with an experimental site like this one. You heard it a lot of times over the last 1.5 days that experiments don't really work without simulation. Usually you simulate before the experiment to see what will happen, and then you simulate after the experiment to calibrate your model to the results, right? WOFEM is a tool that focuses on exactly this kind of work. Sangri, in the second half of this presentation, will show you 3 examples, specifically highlighting how WOFEM can help you by bringing advanced uncertainty quantification methods to your toolbox. So you don't have to code them up, you don't have to necessarily understand every little detail about them. As long as you understand what they are doing and how they can help you, they can bring your calibration to the next level. And they can allow you to do sophisticated uncertainty quantification and get better models in the end. So how does this help you specifically when you are writing proposals? There are 2 areas. I think one is the fact that you can create something and make it available to a large range of people, different kinds of researchers and a lot of researchers at the same time. It's great that Alan just arrived because I want to mention DesignSafe. It's really good if you share your experimental data at DesignSafe, but it's even better if you share your models at DesignSafe. And we have a PhD student who just graduated at Stanford. He designed 40 tall steel building models. That's 40 of the tall steel buildings in downtown San Francisco, the actual buildings. It's not archetypes, it's not like these Mickey Mouse frames, it's the actual building. And he is going to share all 40 of them with detailed documentation on DesignSafe, which is great. But one thing that's interesting about DesignSafe, they have a very flexible schema for sharing things. Basically, you can do whatever you want. You can just dump your data there. By working also with SimCenter and sharing models that immediately run in our tools, you are enforcing some kind of a soft standard on how these models should look like. And the good thing is that it's not SimCenter or DesignSafe who designs that standard, but it's you all. As a community, you say, hey, I really appreciate when they look like this because then it's easy for me to pick it up. So you share it with the SimCenter, then we can share it with everyone that please try to use this template when you want to share models, because that will make it easier for everyone to work with them. And we already see some of this happening, that people start to converge into using the same kind of approach to document and to share their results. That doesn't mean they have to use the same approach to modeling. That doesn't mean they have to use the exact same methodology, right? We want everybody to try different things, to be creative, but make it easy for others to discover what you do. That's what design safe does, right? Make it very easy for you to discover what's already out there, and then pick it up, use what's already there, and only work on what's new, and don't do redundant things, because that's just a waste of time, right? So this is a huge opportunity. We have models being shared, we have methods being shared. Henry Burton developed this automatic steel design code at the UCLA, and we have the automatic reinforced concrete design code developed in Colombia by Carlos Arteta. So both of them have their own research groups. They are working on this. This is not something we developed. The Sim Center cannot do research. We are just enabling research by working with all of you, bringing in your methods and sharing them with others. So these are examples of people reaching out to us saying that, hey, I have a good method, I just published a paper, I want to make it available to others. We make them available, and then we already see them being picked up. And these methods are used, for example, the automatic steel designer is used to enable research on functional recovery. And the guy who is doing the functional recovery related research didn't do the steel designs. He just picked up the method, and this way he could immediately focus on the functional recovery part. And the same thing can happen anywhere in the workflow. So that's the key idea. Now this was the broadening impact part. If you flip it, there's another part which is enhancing intellectual merits. So where you write about the merits of your proposal, if you can bring in methods from others, you can suddenly do more. You can use state-of-the-art techniques from optimization, AI, uncertainty quantification, all of those things. And immediately your proposal looks much better, because you can easily claim that you can do all those things without having to assemble an A team and a lot of additional experts, because those methods are already available in this platform. And again, I listed a couple of examples here how you can use ground motion record selection, which is not as easy as it might sound. And we have that available, so you can claim that you use it in your research without having to worry too much about it. You can use surrogate modeling techniques, which is also something that is very quickly up and coming and much needed for regional assessments. And Sandri will show you a couple more examples specifically on calibration and optimization that are helpful. So one more thing about how this is all running. You have these workflow components, and then we have the desktop applications. And you as a user can decide to use them on your own computer, on your own laptop. We are developing these codes to be platform independent, so they run on Mac, Windows, and Unix. But sometimes the job is just too big. And that's when you will turn to DesignSafe. We are collaborating with them, we have a great relationship with them, and they allow you to run everything with unlimited resources, really. And in our desktop applications, there are two buttons. One of them is Run, that runs locally, and the other one is Run at DesignSafe. That's the only thing you have to change if you decide to run on DesignSafe. You don't need to change anything else about your setup. So you can have a smaller sized problem that you test locally, and then just increase the number of samples, for example, and then send it to DesignSafe. And everything is automatically packaged, sent to the HPC, run there, and you get it back without having to worry about how the HPC even works. This is super convenient. And the unlimited resources is such a unique thing, I cannot stress it enough. That's a lot of money and a lot of opportunities that you can claim. If you are interested in using this, you can definitely talk to Ellen. You can also reach out to us. She can give you a letter of collaboration. We can give you another letter of collaboration, and we can discuss how you can take advantage of our tools or DesignSafe tools. Sometimes it's like you by those discussions you discover additional opportunities that you didn't even think about. So it's best to have those discussions early and explore what is available, and then you can frame your proposal better. And then when you get funded, then you can start working. Now, one more attempt to show show you all the things you can do here. We are doing these high fidelity simulations, right? You do the tests at the shape table, you will have a better understanding of the models that you can build, the numerical models, and then you can see here all the other fields that we are connected to that you can impact. So it's not just engineering, but it's definitely not just structural engineering, but not even just civil engineering. We are talking about urban planners, we are talking about policymakers, so you can really reach all the way to make an impact on society, not just engineering. And that is a really big part of a successful proposal. And we can help you better understand these relationships and who you can work with, so that you are not just making a blanket claim, but you really understand how your methods can make all the way to, say, improving policy for a particular city or community. All right, now, you might ask, okay, how do I get started? So I also have a slide about this. We have a website that has a lot of information. The URL is right there. We also have our email here on every slide, so you can just send us an email, and we are happy to help you. We are happy to jump on a Zoom call and discuss more detail. We have a lot of education and training events, almost every 2 weeks, I would say. We have something online. We have in-person events also, now that COVID is kind of attenuated, let's say. Hopefully next summer also. We do the hackathon with Design Safe, but we also do other events in collaboration with Design Safe for other sites. Like right now we are here because we were invited, and we are really grateful for that. So we try to be there. We try to help make a strong community around this whole NHERI umbrella. If you are interested, you can come as a visiting researcher to our site at UC Berkeley. We can give you a desk, and you can work with us for weeks. We cannot give you money for that, but if you are interested in coming, we give you a place. So that's something, and you can work with the site. You can work with the people who are actually coding these tools. So if you feel like, let's say, you have a student who is talented and interested to put your method into our backend, but you don't want to do it remotely because it's cumbersome, you can send the student to us for a month, and in a month they will code it up. We will make sure it works, and then you have it done. We also have REU positions in the summer. We host 3 to 4 REUs. If you are interested in outsourcing some of your work, and you think that an REU student would be capable to help, let us know, and we can advertise that kind of task. And if a student is interested, we can work with you, collaborate with you, and an REU student over the summer to get something done that can help you. So there are many opportunities. Just reach out to us if you are interested. And with that, I will give it to Sangri to show you those 3 examples that I hope are very thought-provoking. And we will have a Q&A in the end, so please save your questions until then. Please.
Thank you, Adam. So I represent 3 examples related to our tool called Open. So this is one of the 6 software tools we release. So this is basically a tool that enables probabilistic analysis or optimization for a user provide the simulation model. So you provide us a simulation model and tell us what are the parameters that are uncertain. And then what we help you is to run like a Monte Carlo type of forward random sampling to identify the distribution of output, or like to identify what are the important parameters among those unknown ones, and help you calculate the probability of failure of the system, and even to create a surrogate model. And then if you provide us with also experimental data, then we can help you run calculation to update your model. If you run probabilistic calibration, we will give you distributions of unknown parameters, and then you might want to run this for uncertainty propagation again to see how much uncertainty is reduced after you perform this experiment. And there are different kinds of softwares and toolboxes that does this, and why do you use these other tools? First is that we have very nice user interface, and this really helps you, really guide you to all the information that is needed in this analysis. And also if you have, especially if you have, say, OpenSys script that already runs, then really by modifying a couple of lines, you can directly import it into Puff and convert it into probabilistic analysis. HPC resources. And by clicking run and design save button here instead of run button, you can send everything to design save and suddenly use hundreds of cores to run this analysis. And we have parallelized all the UK algorithms, so you don't need to even consider worry about that part. And then we have advanced algorithm implemented that can handle pretty high dimension parameter space and many data sets. And we make algorithm efficient as well as robust. And we are gradually increasing the range of methods we support. Like now we are implementing model class selection and hierarchical based annotation. So basically you bring the FEM engine and we provide you the UK algorithms. It actually don't need to be FEM. Any simulation model that runs in this kind of, actually we have custom here, so it can be any software. And if it's written in OpenSys or Python, it's very easy. And Python means really anything because you can interface anything with Python. And then for the UK method, there are these methods supported, and for each method we have different algorithms. So you can choose and compare different algorithms. For example, if you are on calibration, you have 5 different options, and then we have standardized interface, so you can really click button to test or this, compare all these results. So I will move on to 3 examples. First is soil material model calibration example. Second is reinforcement concrete shear wall calibration. And the third is about how to create reduced order model that can give you similar accuracy, but within much smaller computation time. So our first example is about constitutive soil model calibration. So here we want to calibrate a liquefaction capable soil material model called PM%. It is implemented in OpenSys. It has 25 parameters. And for the experiment, we didn't run any perform any experiments, so we got the data set from design state, which looks like this. And I also want to mention that this work is done by, it was a part of RU project. So we had undergraduate student during the summer. And within 10 weeks, he was able to run all this analysis and create a report. And he did spend a lot of time understanding the result after running the analysis. So it's like, it kind of shows you how easy our tool is to work with. So even undergraduate students can get the result. So our experimental data look like this, and we can have a computational, create a small script that does the same thing, and this can be kind of the result we get from this simulation. And what we are trying to calibrate here is we count the number of cycles to onset of liquefaction. Here liquefaction is defined as 3% of shear strength. And what we are trying to match is this number of cycles. And this number of cycles depends on the vertical stress level, which is represented as cyclic stress ratios. So for each 5 different cyclic CSR levels, we get experimental data and we have simulation results. So our goal was to minimize this gap between 2 data sets. And when we get this kind of test, we naturally have this kind of questions like, what are the important parameters on 25 parameters? And then what are their optimal values? And if there are still remaining uncertainty, how it will affect the response, like in the actual analysis. In this case, we were interested in lateral spreading response. And Copand can be used to have this answer these 3 questions. So first question was, what are the important parameters? And this can be identified by running global sensitivity analysis. Here we have an OpenSys script that can simulate this cyclic shear, cyclic loading test. And by modifying a couple of lines, we can predict Copand and run sensitivity analysis. And this is the kind of result we get. And here it's basically telling you the first parameter. Before that, among 25 parameters, because we are engineers in this field, we can identify several parameters that affect the response. And then we are not sure whether so we have identified these three parameters, like relative density, shear modulus coefficient, and contractional rate parameter from the literature. And then we are not sure whether these three parameters actually affect the response, or only part of them will really affect the response. And that was the motivation of running sensitivity analysis, and our result shows you that the first parameter is actually dominating the response. So when we want to estimate number of cycles, then the first parameter is the dominating one. And in reverse, it tells you that if you have data available with the number of cycles, then maybe it's useful in calibrating the first parameters, but maybe it does not give you as much information for the others. And this can be shown in our probabilistic calibration result. And before that, so what does this sensitivity index mean? Is that so when you fix one of the parameter values and randomly sample these two values based on the uncertainty estimate we have this and run the simulation. So if we plot the parameter versus output, we get this kind of plot. So here we have some kind of trend, but there are some uncertainty because we let these two parameter random. So in case of first parameter, we can kind of identify some trend. But in the second case, because the uncertainty in the first and third parameter is larger, it's hard to identify any trend that depends on the second parameter, so parameter G naught. So it tells you the first one is more important in the estimation of the response. So the sensitivity is nothing but just quantifying this trend into converting this into a numerical value. So the second analysis is based on parameter calibration. This is to answer what are the parameter values of the three parameters, optimal values of the three parameters. So for this, we have exactly the same computational model we use for sensitivity analysis, and now we additionally import experimental data set, which is a text file with the numbers. And this is kind of the result we get in the end. So here, because we ran probabilistic calibration, we have the result of the final the probability density of the final parameters. So if you ran only deterministic calibration, what you get is this particular red line in each parameter. But now we have full density with variance saying how confident we are on the parameters. So as you can be kind of expected from the sensitivity analysis, the variance of the first parameter is the most narrow, saying that we are pretty confident of the first parameter. On the other hand, for the two other parameters, we still have quite wide range of parameters, parameter values in terms of the distribution. So if we ran only deterministic analysis, we know we would have some kind of optimal values, but we wouldn't know how confident we are about these values. So that's what we get from the Bayesian calibration. And further, if you see this plot, there are some correlation between parameter VR and HP naught. And it basically tells you there can be different combinations of parameter values that produce the similar output to the data set we provide. For example, all the combination of parameter represented as blue dot here, if we run a simulation and plot it with data set, they all lie in this dark blue area. So they are kind of acceptable in terms of considering that there are errors in bias, and it is shown in the third example for the forward uncertainty propagation. So now we have calibrated our parameters. We plug it into a bigger simulation model. So we have a whole soil column available, and in the middle part is the liquefiable soil layer. So here we import this model into PubMem, and also we import this distribution into PubMem. We can save this result and then re-import it PubMem. So these are the kind of results we get after the forward uncertainty propagation. So this is the elevation, and it shows you residual displacement, which increases during the due to the reflection. And we see that there are kind of big uncertainty around this point, and this is after calibration, and there were no other uncertainty sources. For example, in our case, groundwater was even fixed. So even after calibration, because of this uncertainty in the parameter values, we still get this kind of variability in our final lateral spreading response. So what I wanted to tell here is that if you run only deterministic analysis, you are saying that one of these blue possibilities as your optimal, and then if you put structure on top of this, and then run damage and loss analysis and recover simulation, you just accumulate so many errors in each step. So it is really important to run probabilistic analysis from the step of calibration. So that was like our first example we had. But we know that in the real world application, it's not always easy to run this probabilistic calibration, because to get this result, we had to run several hundred of simulations to calibrate these three parameters. And if your simulation is long, then you might just want to run deterministic calibration, and that's our second example actually. So in our second example, we wanted to calibrate the material model parameters of RC concrete block. And here we again have cyclic loading test data, but with the full model of the reinforced block concrete wall. And therefore our computational model is again the model of four components. And I want to mention that this work was done by Professor Lowe's in University of Washington and Hershey. So here they wanted to calibrate this parameter using from this cyclic shear test data, and they wanted to match the deformation capacity, which is defined as the deformation where this wall fails. And there were two failure modes. First was the complete compression buckling failure, and the other was rebar tension fracture failure. And for each failure mode, there were one dominating parameters. For example, in concrete compression failure, the concrete crushing energy was the dominating parameter, and for rebar rupture failure, steel rupture strain reduction factor was the dominating parameter. So they want, for each failure cases, they wanted to parameter one of these, calibrate one of these parameters. This example seems to be very similar to the previous one, but there are different challenges here. First is that the model was expensive to simulate. Here, this was very detailed model, so it took 3 hours per each simulation, so we could run thousands of simulations. And second thing was kind of unique. So instead of the Bayesian, they tried to use gradient-based algorithm, but then they realized that their error function, the objective function for the calibration, is they look kind of like this red function. So it's almost like a staircase. So they can can evaluate the value at the point, but the gradient information was not available, so they couldn't use gradient-based algorithm. And Puffin had gradient-free algorithm, so they decided to use that. I will skip this part. This is the detail of the data set. So they got data set from design set, so they didn't need to do any more experiments. And then they had computational model with the pieces with these two major parameters. And the first step before calibration is to run forward analysis, forward uncertainty propagation using Monte Carlo simulation to understand the problem going depth. So what they did was to import this concrete model to Puppet. It's 3 hours each, and they generated like 50 samples. So if they ran this in local computer with say 8 cores, it would still take a full day to run this analysis. But they sent it to design stage and then use 50 cores so that they can get all the results within 3 hours. And this is kind of example. So it's using parameter value versus the error level. And by running only the forward propagation analysis, they were able to identify the parameter values that gives the smallest error. And this can actually help them complete the calibration test. But the problem of this approach is that it's not very efficient. They require many simulation for that. And still, we are not sure whether this value they got is optimal value, because by chance, we might not have sample around here that we will miss the optimal values. And then this approach is not scalable because if dimension increases, the number of samples required for this exponentially increases. So we need better algorithm for that, such as this gradient-free algorithm. So here I will use the same model and same data set and go gradient-free algorithm to calibrate these material models. And as you can see here, with using smaller number of analysis, it was able to identify the optimal parameter values. And this gradient-free algorithm is useful for different kinds of objective functions. For example, when your objective function is kind of discrete, or when you have noise in the objective function, then it can still be used. Gradient-free algorithm can still be used. And the third example is the different. Here, Puppet can be used to create a reduced global model. So the idea is when you have a physical experimental data, you might want to first calibrate the best model you can make, the high fidelity model you can make, which might take long time to run each analysis. In that case, it's great that we have good accuracy, but it's hard to apply this to other analysis because it takes long time to run. So what people like to do is to create a reduced order model that gives you similar accuracy of the predictions, but runs in with like a second. And then how to reproduce that is to run this analysis 700 times, like for seismic risk analysis or risk performance assessment, or even when you want to model the source structure interaction, then you might not want to bring the high fidelity model, but the one that runs much quicker. And so here we use, again, Bayesian calibration method to calibrate this reduced order model. And this is just an example of how reduced order model can be structured. So when we have a high fidelity finite element model, there can be a degree of freedom of interest. Here we have this, for each story we have total 9 degree of freedom of interest. And we have a simplified model that looks like this one, which again have 9 degree of freedom. And in this model, there is a string everywhere, which is to capture the linear range of this response perfectly. And then the non-linear range is complex, and there were 36 parameters to be calibrated. And these are the calibration results. As you can see, compared to before calibration, of course, the accuracy is quite good for this 3 ground motion we use for training. And also because we use baseline calibration, we had all the parameter values in terms of probability distribution. I'm showing you only the first 3 parameters. And then what we did, and the next step is to run seismic risk assessment using the reduced order model. So we imported reduced order model as well as the calibrated parameter values into EUQ instead of POFEM. So we could have used POFEM, but we just chose EUQ because it additionally has this ground motion generator. So we didn't want to bother this part, so we just selected this stochastic ground motion generator. And by providing the 3 values, it automatically created the ground motion time history. And of course, we have standardized interface, so we can directly import this model, and it will automatically run the analysis and gives the result for its POE. And this is kind of the result we get after running EUQ. So as the threshold of peak inter-story drift increases, the exceedance probability decreases. And we are also showing the result obtained by running original model, which is 100 times longer. And considering that this order model was showing pretty good performance. So POFEM has it easy to use user interface, and it is super easy to use design state HPC resources using our user interface. And our algorithm can really help you to overcome the challenges you face during the calibration process. So I hope you want to check out what kind of algorithm we support. And also I hope you find more opportunity to share your research and also make use of other people's contribution to our center sector. I think that concludes my presentation. Thank you so much for listening.
All right, so we have one more presentation, and then we'll have Q&A for all of the different speakers from this morning. So the last presentation is by Farouch. He uses his own computer. He's going to talk about the IT resources available, data acquisition system, sensors, etc.
Hi everyone, for those who don't know me. I'm Kurosh, and those who know me, hi. Those who don't, very nice to meet you. I'm going to briefly go over the IT resources that we have, the cyber infrastructure at the LH06, and the data acquisition, the sensors, whatever will be available to you, the users, the future users, hopefully, of our facility. Now, Just to briefly recap what's already been said in other presentations, we're a pretty small group at the shake table that LH sits. There's the PI, Professor Conte, who is not here with us today. There's 4 co-PIs, each with their own responsibilities in their respective categories. And how I fit into it is I'm the operations manager at the facility here. I'm the shake table operator, the data acquisition expert, the guy who handles the sensors and all day-to-day activities. So hopefully when it's time for you guys to write your proposals, talk to me. I'm very easily accessible. Just reach out to me. I'll gladly help out with whatever I can. So just trying to make this presentation a little quicker, so I'm going to go a little fast, and then if you guys have questions, please ask at the end of the Q&A session. But the infrastructure that we have, the IT infrastructure and the security in our facility is paramount. It's very, very critical. The data that we get from the tests are very sensitive. We definitely don't want anything bad to happen to them. So we have a UPS system, for example, for power. We want to make sure that the data acquisition system gets clean power at all times. We don't want any power fluctuations or any noise that's coming through the power to contaminate the very critical data that you're trying to collect. And also, the UPS system will act as a buffer. If there is a power outage during your test, you don't want you to lose all that data. So at least we want to have enough power to save and close and shut down the system properly without losing anything. So we got the UPS. We also have offsite backup and redundancy. We not only back up to external drives locally within our facility, but we also have secure backup offsite in case there's a fire or some other natural hazard that may wipe out our facility. We don't want to lose all that data. Of course, at the end of testing, we provide the user with a copy of the data, the raw data, for you to upload to Data Depot. And we also keep a secure copy for ourselves if the user loses it or something happens to their copy, and reach out and provide the data back to them again. Our facility goes through regular audits, weekly audits from the campus, the main campus IT department, and also Robert, our IT manager over there, does vulnerability testing on our network pretty regularly to make sure that everything's in order. And on the physical side, we do have locks on all the doors, and we have security cameras and alarm systems in place to give us any kind of alert notification if something bad is happening on site. The site, what's available to the users, we have gigabit Ethernet throughout the facility. We have secure Wi-Fi anywhere you go. I know we're a pretty large facility. You guys came out there yesterday and saw it. There's a lot of land, but you have Wi-Fi pretty much anywhere you want. There are a few spots that you will never go, but they don't have Wi-Fi under the table. Maybe you might not have a good connection, but generally speaking, while you're on site, you do have internet access. The main systems on site, like the control system for the shake table, the data acquisition system, they're on a separate network. They don't go on the internet. They're not accessible from anywhere but the people who are allowed to use it on site. So we do have separate networks. There's the networks that are externally accessible. So if you want to access your email or Google Drive or collaborate with any partners, you're more than welcome to. But the other network that houses the secure devices that we have does not access the equipment that we have is very sensitive to run the shake table. There's a saw, hydraulic equipment, the control mechanism, the accumulators, everything. We have to make sure that everything's running in tip-top shape at all times. We need to be alerted if there's any kind of condition in advance. We don't want it to become a catastrophic disaster. So we have real-time monitoring for any of these subsystems that we have. For example, on the screen right now, when we talked about this briefly in our tour yesterday, those 75 large accumulator bottles that we have for our accumulation system each have the sensor node installed on them, where we monitor the temperature and the pressure, various things. In real time, we store that data so we can do historical looks and see how, if there's any kind of leakage or if there's any issue with the system, we can identify and correct that before it becomes a major problem. I did mention this a little briefly yesterday, but in case people didn't hear, the pressures in these accumulator models do fluctuate throughout the day based on the temperature changes in the day. So having this kind of information is very critical. The monitoring system that we have now looks like this, where you can see, this is a pretty decent figure here, where this is over a few days span. It's kind of a bigger picture, where you can see at the top here is the pressure in PSI. You can't read those numbers, I assume, they're pretty tiny. But you can clearly see that it's a pretty substantial change with respect to the temperature, which is this one. So throughout the same time period, you can see as the temperature increases, the pressure increases, naturally, pressure drops, temperature drops. Some various factors below here in this presentation, but we do monitor these and store that information in a database. All of this is happening locally, by the way, on that network that's not internet accessible. Aside from the accumulation systems, the cooling tower, and this was also briefly discussed during our visit yesterday. The hydraulic fluid that we use is very sensitive to temperature changes. We don't want the oil to exceed a certain temperature while we're running the shake tape. As the temperature increases, the properties in the oil will change, and it could potentially damage the equipment. So we have a large cooling system that continuously cools the oil that's running through the system, but even that we need to keep an eye on and make sure that the heat exchangers are functioning properly and the temperature at various points along the system does not exceed what that set temperature is. And if it does, if we see we're approaching that limit, or if we are about to exceed that limit, we need to shut down the system and allow for this cooling tower to do its job, cool it down a little, resume. So we do have a monitoring system with various sensors in place along the hydraulic fluid cooling system. Aside from that, we have what's called the Echo Health Monitoring System from MTS Corporation, the company that makes the actuators and our hydraulic pumps that we were able to see yesterday. The Echo Health Monitoring is a system that's with a bunch of sensors placed on each one of those large pumps that you saw that apply the pressure to the accumulation system and the shake table. We have various sensors in each one of them, and they're all connected to their own subnet, and has a portal where we can monitor the temperature inside the HPUs. The pumps are called HPUs. The heat exchanger in each one of them to make sure there's no water that's leaking. If there is a problem with one of the heat exchangers, you definitely don't want the water to get inside the oil. We need to keep a close eye on the water saturation. We need to keep a close eye on the contamination. So if you have particulates, if there's dust or debris, we are an outdoor facility, so there's plenty of dust. There's construction happening right over this equipment. We have plenty of filters in mind for the oil, but we definitely don't want any kind of contaminants. So we have many sensors throughout as well in these HPUs, which keep an eye on the contamination levels of the oil. And if we see that the contamination is increasing, we will stop and make sure we filter that oil properly before resuming. So having this kind of monitoring system in place is very critical, and we make use of it daily. The ecosystem looks at other metrics as well, which I'm not going to get into for the sake of time, but just to give you a notice that we do have. Now, the main part that is for you all is the instrumentation and the data acquisition system that we have available for use for your future projects. Our main objective is to provide quality data. I mean, the data that we give you from your experiments is unquestionable. We give you accredited data that you can be sure is good and reliable. We do have plenty of documentation that outlines the things that we can do, our calibration procedures, the various reports that we have, and equipment history and inventory. They're available on our website. I'll get to that in another couple of slides. But the primary objective here is to give you quality data for your work, whatever it is that you're testing. We have a whole lot of sensors available, all sorts of sensors from MEMS-based accelerometers, 251. I mean, you can read these numbers, I'm not going to read them out, and you have these slides, they're available to you. We have a lot of accelerometers, and these are very popular for seismic testing. They go, a handful of them are plus or minus 5G. The vast majority of them are plus or minus 10G. A lot of linear displacement transducers going from those tiny little 1-inch ones going all the way to 20-inch displacement. We can measure those. String potentiometers, gigantic ones going 120 inches displacement. So we have that all covered. We have inclinometers, load jacks, load cells, soil pressure transducers, a whole lot. We're currently developing our newly refreshed GNSS system, which is we have 10 receivers. For those not familiar with GNSS, it's basically GPS, but you have access to more than just the American satellites and GPS. You have access to satellites from the European network, and the Russian network, the Chinese network, all sorts of satellites. So it's called GNSS. We have 10 receivers. They're going to operate at 100 hertz. That will also be available to you for very tall buildings, like the one you saw earlier. At the 10th story, how are you going to measure the displacement of it? We can't really put a string pod. There's no reference tower. So these GNSS receivers will come in handy for measuring roof displacement, for example. We also have the drone that Robert operates back there. You just saw a couple of cool videos of that earlier. We have a lot of cameras available to you, and I'll get to that in a couple slides. We can synchronize all of the cameras to go with the test. So when we give you the data and give you the video footage, it's all going to be synchronized. It's pretty straightforward. And we, of course, have an end-to-end live streaming service where you can stream your tests, getting publicity, and disseminate that to the community. I forgot to keep clicking next when I was doing this, but you get to see these pictures of these things now, so sorry about that. Now, the data acquisition system, what all those sensors connect to. We had an old data acquisition system that served us very well for the past 15 years of operation. But it was getting a little old. Some of the channels and the components were starting to fail, and they're just obsolete. So we were one of 3 selected by the university here for an MRI proposal. And it was this very highly competitive proposal, but we got it. And we were awarded, there's some details here on the screen for that award. We're very grateful to get this award. We were able to build a new data acquisition system that we're expecting to live on for an additional 15 years for us here. The new data acquisition system is comprised of 13 nodes, we like to call them 13 machines. They're all bundled together, and I'll have another schematic on the following slide. Each one of these 13 is capable of hooking up and measuring from 64 different sensors, user configured, so you can put accelerometer, the next channel order, the strain gauge, you can do whatever we want, any kind of bridge configured sensor. And if you're not familiar with any of this stuff, I'm your guy. We can talk later, and I'll help you through it. It's 24-bit, the entire system, and it's capable of 25 kilosamples per second, simultaneous sampling per channel, and it's readily scalable. So hopefully, as the need arises, we need a 14th node, we can just purchase a 14th and stick it right into the system and add to our capabilities there. The basic schematic of what they look like, I don't want to get too caught up on this, but this is what we call one node. So when I say we have 13 of these, it's 13 of this whole system here where we've got a chassis, a controller, we have these bridge configurable modules, some rack mounts, and some cabling to connect. And that would be one node, and we have 13 of them. And they're connected to their own network. This is not on that public network. A better diagram than this is here. The way we've set it up, most researchers for most projects won't be using all 800 and some odd channels in this data acquisition system, except for this Tallwood building, which is using every last channel we have available. But generally speaking, most projects won't be. So someone might have a project that only needs 200 channels or 300 channels. So the way this data acquisition system is set up, instead of having all of them daisy chained together to make this one gigantic system that you have to turn on and turn off every time they're separated into 3 stacks. And this kind of shows those stacks. Cute name, Pixie, because the modern numbers on the side, whatever. So we have Pixie A, B, and C. Each one of them has, well, A and B have 5 nodes each, and C currently has 3, but we can expand and add another 2 in this stack at some point. Now, these stacks can be individually operated. So if you have a project coming in and you're like, I only need 300 sensors, I'm not going to run all 3 stacks. We'll just use one of those stacks and keep the other 2 powered off, so we don't, put excess wear and tear on them, only when needed. So the way these are all hooked up, the Shavetable controller has a separate line that gets connected to each one of these stacks. That's for the triggering, so when we hit run on the test, the data acquisition starts to record. When we stop running the test, the data acquisition system stops. So your data is synchronized with the table movement from start to finish. Similarly, the Shavetable controller has another trigger line going to the video recording system that Robert manages, where all the cameras that are filming your test start and stop with the Shavetable and with your data. So the video footage that you get and the data that you get will all be synchronized together. And all of this goes to a local switch and a dedicated machine that manages all this stuff. This part I'm going to kind of go through pretty quickly because you can't really get anything out of it, but the software, I developed it in LabVIEW. For those familiar with LabVIEW, I don't like it. And it's not my jam, but I figured it's a good application for this. It gets complicated, the schematics, just put a few things up here. But it was a huge effort putting it together, but I'm proud to say that it's done. And it's ready for you guys to write your proposal. Lastly here, moving on, I said I'd bring this up earlier. We do have a couple of websites, and we're on social media. You can find us at DesignSafe. The link is here. It's linkable in the PDF that you have access to. There's a navigation bar at the top where you can go through. There's a lot of information, documentation, what's available, our sensor inventory, etc. Everything can be found here. Contact information if you need to reach me. For those who don't know how to contact me, or any of us, I should say. So we have the DesignSafe website, and we have our own local website, which has pretty much the same information. Here, we have this similar navigation toolbar that you can go through and find our information. We do have live streaming cameras at all times on our website. There's 3 cameras. Currently, if you were to go on our website right now, you'll be able to see the building. And it's live stream where you can just spy on me and see when I'm slacking off. You can just, I'm not Krish, you gotta get back to work. Our website is being updated, so we're gonna have a brand new website coming up, hopefully early next year. So, stay tuned for details on that. With that, I do want to mention one thing that Lely mentioned earlier. We do have a workshop survey. It would really help us out if you guys can take a minute at the end of your day, whenever, and just go take our survey really quick and tell us what we're doing well and tell us what we're doing poorly. We'll make it better. It's completely anonymous unless you want to give us your email address, if you have something that you want us to reach out to you for. But if you have a second to scan that code, scan it, keep it in your browser so that way you can fill it out later whenever you're done. Again, this is also in the PDF that you'll have access to, so feel free to do it later as you wish. But that is all I have. I'm just going to leave that on the screen and hand it back to John. Thank you.
Another housekeeping item, which I forgot to mention during the beginning session yesterday. We've offered several of you travel, or all of you travel assistants to attend this workshop. The way that we're going to handle this is if you could please send Rush and I an email with your receipts. We understand that your travel probably was more than the amount we offered you, but we had 4 or so cancellations, so we're going to try our best to offer more than we initially offered. So hopefully we're going to try to help you out. And then just so that you're aware of how it's going to work, forward your email on to Shannon Lardot, who is our departmental staff, who helps with reimbursements. She will help guide you through being added to our procurement system or vendor software, one of those, into our system. And then once you're added there, it will get processed, but because we're right at the holidays, there's going to be they're closing for basically a week and a half. So expect your reimbursements to probably come at the end of January. So I hope that that's reasonable. If you do have a rush, just note that in your message, and we'll try to put it through first. Is that okay? So I know that a lot of us have questions of the speakers this morning. So right now we have an open Q&A session. I suppose there's a mic over there to get started. Maybe I have a question for Adam. Stepped out. I suppose I could ask a question for Link. So going on the Crucia's presentation for the instrumentation, when you have such a large structure like that, and you have so many different teams coming and doing projects, how do you decide on the instrumentation plan, and how do you prioritize sensors in different locations?
Yes. In fact, our project we have a major, three portions of the instrumentation. One is non-structural, and one is the gravity system, one is the lateral system. What I did is actually first go to the site, see how much channel you have, and then internally it's almost like a competition process. I just tell my co-PIs responsible for that portion of the work, have them kind of divide it up. Everybody will kind of give me initially first round. Everybody will give me added up. It's like over 1,000 channels. Then I just look at it and proportionally have them scale back until we fit the site's capacity. Then as for at my level, I focus a little bit more on the gravity system because I work on that. But for the other systems, in fact, I don't really know too much. I just give them a total number and they figure it out, and then we have meetings to talk about, try to kind of do that, negotiate within your team, within the site implementation.
When a follow-up on that, when you're planning your proposal, did you think about like instrumentation racks, the places where the instrumentations are going to be mounted?
At the proposal stage, no. I mean, at the proposal stage, we know what is the scientific question or the answer. For this one specifically, the rocking wall, the performance, and then the non-structural damage. Yeah, we know we will have instrumentation there, but at the proposal stage, you don't need to. I mean, for a project this size, you don't need to provide too much geographical instrumentation. But if it's a smaller test, like 1 or 2 story, I think providing that will likely help you plan it better. But for a project of this scale, it's simply not possible.
So, Karush, maybe if somebody were to build a building, where does the support start and end for? So you're providing the instrumentation. You also provide the rack where the instrumentation is. If you have like a stationary reference frame.
Yes. Hello. So we provide assistance with figuring out where to put your sensors, or helping, guiding you if something is not possible, if we think it's not feasible. But we also provide those safety towers that you saw yesterday. We can use those as reference towers. So if you have a strain pod or some instrument that you want on a stationary point of reference, we can assist with putting those where they're needed and installing your instruments. Aside from that, we have all the cabling required, the sensors required. The one thing I didn't mention, and I think it's worth noting, strain gauges are considered as consumables. So they are the responsibility of the project team. We don't stock any strain gauges. So if you have some pages that you want to put on your stuff, we can refer you to the place where we buy them. They're pretty reasonably priced, but that's going to kind of be how you. Aside from that, the list of instruments that are in my presentation, and you can find on our website, we provide all of that.
What happens if instrumentations are broken during a test?
Great question. If we hand you working condition instruments, we expect to get them returned to us in the same condition they were given to you. If any do break, and this has happened, because it's an experiment, it's something like crash and fall on it. You just need to get reimbursed for that or replaced. So I would advise including in your budget, depending on where you're selling instruments, especially if it's like a geotech project. I think they go through instruments a little quicker than others. So I would advise putting a little bit of money, setting it aside in case you do break either cameras or instruments in the sensor. Set a little bit of funds aside for that. But if you do talk to us early enough, we can guide you, maybe give you some advice on, oh, I think if you put the instrument here, it's gonna break. So maybe we can help you out and give you some advice on how to mitigate that.
All right, so other questions?
So maybe for modular test bed building, so I just want to know if you have any existing drawings or information, detailed information about the building without maybe the testing yet?
Yeah,
So-
there's drawings available for the configurations that Lisa's done, and those of course can be modified, but we do have drawings available.
Okay.
Those will be, once the data set is published, those will be like more easily accessible. If you're interested in like working on a proposal, I think we could look at what we could do to provide those.
Okay, and in terms of proposal development, if there is a need for some of the data before you publish it in design stage, to just make a baseline comparison maybe with some other.
Yeah, no, I think if we're starting to work on a proposal now, I mean, I'm hoping this data is published within the next couple of months and it'll be available. But if you need anything earlier, reach out to us and let us know exactly what you need. Like if you need drawings, then you should be able to provide those drawings.
I have another question for the mass timber project. You mentioned that your phase will be after demolishing four stories, you're going to be testing the 6 stories, right? Do you expect any damage in the wall while rocking in the first stage when you have 10-story? Plus, do you have any plans after you finish the 6th story to do any additional stuff or maybe collaborate on other stuff? Or is it going to be tied in time for the following testing?
So first one, Link, are we going to have any damage?
No, taking
So
it-
right now, no, in terms of, more with jokes apart, if there is some damage, we'll replace. But if you do notice, we'll repair, and that's part of the work as well. But if you do notice, the toes of the walls are heavily reinforced. Part of it has to do with the design, but part of it is because those walls were designed to take many earthquakes. And so we are mitigating any potential damage at the corners of the walls. We are going to be replacing elements, so the UFPs are all going to be replaced. We're expecting those to be damaged. I think you asked some questions about that as well during the visit yesterday. So there's that. On adding additional things to the 6 stories, we're really tight right now in terms of timeline. We have agreed on a deadline of when we have to be out of the shake table. If you walked around yesterday, you probably saw a big white tank-looking thing. That's waiting for us to leave. So right, the moment we can, everybody will be really excited that we do leave the facility. But with that said, there's huge opportunity still for collaboration. because there's only so much we can do even after we're out of the shake table, right? There's so many lessons learned that hopefully it is the true capstone project where people would be able to use the test results, some of the models that we're developing as part of the design, and we're doing some predictions, we will be doing some post-predictions that was mentioned here. But yeah, so ideas that you may have, not only we're happy to collaborate and we can be involved, but we don't have to be involved either. Just let us know what you need for your future research and we're happy to share. Thank you. Also happy to share lessons learned. Ling, I'm sure, and I have been contacted by folks doing research in steel, for example. Nothing to do with mass timber. But, okay, how did you add additional masses? What do you do for torsion? And, you can ask us, you can also ask folks here, right, that have experience and have done many, many other tests, also UCSD, who are happy also to share that information. There's the thing that I've learned over the time, the worst that there can be is, you get to the site and you're always asking the same questions that we may have already asked. So call, email, we're happy to help. Did I say anything?
That's fine. Perfect.
Maybe I have a question for Adam. So I know the STEM Center is mainly geared towards research, but many of us teach courses. Do you have any examples that could be used as part of class projects, which could be considered training for future users?
Yeah, actually, thank you for this question, because this is one more thing that just didn't make it to the presentation. We do have a gallery that we started a few months ago where we feature materials that were used in courses already that you can use as templates for your own courses if you want to teach something related to simulation in natural hazard engineering. And we are planning to grow this as long as we have other people who are teaching and who are happy to share what they used. We have the assignments that were used in the course. We have the input files or the files that are the starter package for students. And we also have slides when they are shared by the instructor of the kind of material that was taught during the class. And as more and more people pick this up, for each topic we would have, we imagine as a vision, we would have multiple ways you can teach that topic depending on how deep you want to go in one area or the other. So that's where we want to get. There's a lot more interest right now in performance assessment. So I think we have 5 courses now in the country that use our tool for performance assessment kind of assignments. We have 1 course for regional simulation, 1 for earthquake response estimation for structures, and 1 for COFEM, uncertainty quantification kind of things. It would be great to have some geotech things in there. So please let us know if you want to teach. We are also, one thing I didn't mention is that the postdocs we have, we call them software developers, but they are so much more than that. They are domain experts. They are experts in one part of computational modeling, and that expertise is available to everyone. So if you want to do some modeling and you just don't know how to get started with some part of it, you can reach out to us and we can assign a postdoc to your project, not 40 hours a week, but a few hours a week for some weeks. And that can really make a difference because it helps you get started, it helps you navigate a new field perhaps, and helps you not only understand how to use the tools, but what is the theory behind it, and what are the methods, what are the choices that you have. And these same postdocs can also help you with the educational things. So if you want to teach a certain thing, they can help you understand what tools we have that could be supporting students learn, and they can help you prepare the input files or the starter package for those tools. And you don't have to share those back, but if you do, we appreciate it, and then we would feature it in the gallery. So that's the cycle that we have. Thank you for the question.
Thanks. Can I ask a follow-up question?
question on the, so regarding the, it's probably a high level question, the geotechnical capability, modeling capabilities right now at Sim Center. So my understanding, we have used OpenSeas, but it's probably designed initially with structure modeling purposes. So in terms of geotech capability, like retaining walls, foundation modeling, 3D soil elements, what's like status?
So OpenSeas is of course supported, and I know that it's not necessarily providing all the features that you guys need. Because we have this general Python wrapper available, you can wrap it around any kind of code. So if you use another tool, you can interface with that tool through that Python wrapper, and then you can use that tool in our workflows locally. When you use our workflows on DesignSafe, you want to have that tool available on DesignSafe. So depending on what tool you use for your geotechnical work, you need to talk to Alan and make sure that it is available on DesignSafe. There are no limits, I think, in general on what they can make available. Sometimes you have a license issue, but if you have your own license, I think you can work this out and then run those tools on DesignSafe as well, except for those that do not run on Unix.
Right.
Right, that's an important caveat. So some tools, just give you an example, Deep Soil. I think Deep Soil runs mostly on Windows, or maybe I'm wrong.
Oh, they have a version that runs on.
Oh, there you go. It's a bad example.
I'll give you another example.
Yeah.
Like FLAC, you know, like and some of the code.
Yeah.
If you don't mind. Some of the codes that we, the geotechnical community have adopted, like FLAC and Flaxis, have not. Well, let me just say, when we last approached them about trying to integrate them into the HPC environment, they just weren't ready. Because most of their users are in consulting, and they are very much Windows-based, they just focused on that. I think those companies may be coming around. I was at a conference recently, and Rock Science was talking about some of the stuff that they're trying to do moving forward. So there may be opportunities on some of those geotechnical codes or programs that we use. I still use OpenSeas just because I know that it runs, it's got some good models, it's got good structural models, so it's the easiest to use in this environment.
Maybe can I add one more thing, just a little thing. Some of you might have your own cluster. So just a workstation, maybe a stronger computer that you use to do these calculations. SimCenter tools work on those. So if you have these software available on those computers, you can still experiment with our tools, and you don't have to go to DesignSafe. We encourage everyone to work with DesignSafe, but maybe as an intermediate step before these things get available there, you can still start experimenting with the tools we have.
We'll have a lunch here. Continue discussions there. I do have some closing comments. So we're actually going into the mode where we're going to have 2 workshops per year. We're going to have our user training workshops in December every year, but we're now going to also be having a second industry academic workshop. So I think we're going to be planning in late spring on this, so maybe April to May. So if you're interested, come back out in San Diego. Weather's sometimes a little bit rainy that time of year, but it's also nice. But that could be a good opportunity to meet some of the companies and government industry, government agencies who are wanting or are interested in large scale shake activities. So that's coming up. We'll definitely keep you on our email list, so you'll probably see the announcements for it. If you're interested in submitting proposals, don't hesitate to contact us. Any one of the people on the project team, Krush, myself, Joel, Lily, Michelle, or Jose. And answer any questions that may help you to enhance your proposal. And there's no obligation, again, to involve any of us on your projects. We want you to be successful. We want to enable you to use the site and get good results. And there is a schedule of tests that are upcoming, and the earlier you start planning, we can put you into the queue for testing. There may be creative ways where we can put you together with other tests to go. So with that, unless there's any other questions, I'd like to thank you all again for coming and taking your time, especially in the holiday season. You know what I'm saying?
Just so logistic.
Oh, yeah.
For the slides, for today, or we're going to upload it.
Yes.
You'll see the same thing. And one more thing I forgot, a lot of people took photos yesterday. Are they going to be able to upload to that folder to share this? Or
Sure.
Yeah.
So it's an open drive.
Yeah, that same link that everyone has access to, there will be subfolders within that link. Right now, I think there's one that says presentations PDF, or one that says pictures and video, or one, yeah.
Because I didn't keep any photos.
That's good. Good point. So when I'll send in an email about reimbursements to everybody, basically saying what I told you here, because several people had to leave earlier anyways. And I'll put the link into that email. Maybe I'll go over it with Rich.
And I can send an email when everything is completely uploaded, and so you can check
And
it.
you don't download it and have to go back and download it. So again, yeah, thank you. Box lunches should be outside.
Nice seeing you as well.
Say hi. Are you at the meeting? Yeah.
My wife, so that she's okay that I'm in San Diego. Right? You have to negotiate time with your family.
More
as well.
difficult negotiations than the other ones.
Oh, for sure. Especially with the timeline.
All the ladies, you're gonna know to them all about.
Yes, I was there for the first 5 minutes.
I wanted to ask you something. On the hybrid, how big can you go hybrid from us?
You want this up to here?
Yeah.
We had a pretty big incident on that.
You gotta, what do you call it? You gotta
Or just providing.
But, well, yeah, I don't know.
So, yeah. It's very exciting. We're starting now.
But yeah, we basically control.
Yeah, but anyway, that's the first phase, right?
Yeah, like, you can control the table.
Kind of old.
You want like a build thing?
Yeah, figuring out what you can do. Or even have structure, another activator that is connected to something else.
Thank you so much.
Over the next one, actually.
Looking forward to talking.
That was another thing that when we did it, we had a limitation in that there was no outlet to the pump, and they had to upgrade the hydraulic system. Right now, there was only that additional donation for the reaction. Here, I had an external pump. But we're going to get an outlet where we can. But I would just bring it up to really have. Like, I'm not part of that.
Oh, yeah.
Hello?
No, but at the university, right? Right, exactly.
Yeah, so we talked about it at the beginning, but I don't know.
Yeah.
We had a pretty big incident. turned out to be a faulty part, but we still have to luckily we have like
Maybe we should be walking and talking about it, right?
Yeah, is there still some research needed for integration, or is this?
No, I think if you really want to do something,
Already crucified. Yes, of course. There was
So maybe right now there's a lot more.
Yeah, it should be straightforward to do it. For the also we have the flex test control.
Yeah, that's cool. Jobs is at
So,
daycare.
it's up to you.
Yeah, we can talk about it together. I mean, it should be straightforward to implement.
Maybe still breastfeeding.
For example, imagine
That's it.
it's a rocket system. So you could model that and then even if you have a rocket system, it's rather simple just system that you can model and incorporate that.
This is like an Eastern.
And then model just
Like I know
base but you would need to add actually
Yeah, that's kind of what we wanted to do.
Grandparents.
That's the hard world connection. If the hard is straightforward, different. As long as it's allowed. Yeah, we'll have but these are things that we talked about. I said, yes, we're going to know we're not in the end. I don't know what kind of make it if it hasn't, then it should. I haven't been up to the site.
And you'd have time to be interested. Yeah. Start small.
Yeah, I was trying to get like, something on the SRD where I do get that. We're upgrading the right. Also like a shake deal.
Yeah.
Many citizens come through here, they were going to.
Yeah, did a lot of barbecues, a lot of basketball games. Yeah.
You take it off, or?
I'm gonna still be around. I'm going to see Benson.
Oh, okay.
But we will be in touch. So
Yeah, you got your part done already?
I'm gonna be responding tonight.
Alright. Maybe I can see tonight. Yeah, but that'll be the first thing. Make sure I have. And see what components, especially for next year actuator. Like, yeah, that might require some more hardware. Yeah, I don't know if the current system is compatible. They have a flex test, it's pretty new, so it might be compatible. So they sell that hardware.
Start there.
Yeah.
You can actually around lunch.
Nice to see you again. Keep me informed.
To be honest,
So you're gonna be testing up here.
And it's more or less the same students that are doing both. So to say after mid-January to wrap up
communities
so it's going to be
around
end of January, early February. That can give you a little bit
That
more.
might be something else.
If you have time,
Like,
you can figure
can
out
show that you have a real application.
for you to just check
And then
all
they
of
will
that.
value the computation you do.
We have like map templates developed or that we developed for checking the design. But it's me having somebody like you just peer review it. Yeah.
Let me ask Karush about that and I'll get back to you.
Yeah.
Exactly.
Right?
You already have.
Yeah, they probably trust the finite elements in your fall rupture. Holy horrible.
I would also trust a simulation to do exactly
To do, right.
Like, I wouldn't consider those simulations. Maybe, I'm trying to give it a terminology, and I'm trying to think like virtual experiments, that's still like a simulation.
Yeah.
Two separate things. Yeah, back to the site?
Are you guys all heading back? Yeah, totally get that.
Go hang out in what's that?
Oh, the great. Yeah. Is it the one in the middle of campus?
The big,
It looks kind of like this.
Yeah.
It looks like just a concrete building. Oh wait, every building. Yeah. Yeah, it's tough. We have some red eyes that go to Texas. It's like 3 hours, at least if you're going all the way east. You get a little bit of time. If you can sleep.
Unless I stay.
Data and then Wow, Monday. When did you guys end classes then?
This past Monday. So we
Oh, but did you have this huge? Oh, the 12th was your last. Oh, yeah, ours is the one. Oh man.
Sure, actually, this workshop kind of fit in.
Yeah.
We're off.
They just.
I know. Forward to that.
They just changed our calendar that we're starting a week earlier, so we're back tonight. And so we never end. They decided we got all of Thanksgiving week off, so that made our fall 14 weeks. And then they're saying, well, now we need the spring to be equivalent, so that's going to be only 14 weeks. So we're starting early, and it's 1 week shorter. So we're going to be done before May. No, we're in semester. Yeah, that's what we always were.
We cannot go anywhere.
Yeah. What's nice in Austin is like the spring breaks are coordinated between all the school districts and the university. Yeah.
Our middle school and university they have different.
Yeah, that's rough. That's horrible, actually. I think that should be illegal. In a college town like that? Come on. I mean, we're in a big city with a college. Okay, yeah, the beginning, yeah.
University does not start until late August.
Right.
So what are you doing with your family here? Gonna go see SeaWorld or anything?
No, I don't get to see them all that often. It's like a cousin, right? You know, and so I'm just gonna go down to their place. They have like a Christmas party, ugly sweater party to go to tonight, and I'll go with them and just hang out, really.
Okay, that'll still be fun.
Yeah, exactly. My aunt and uncle are gonna be here to visit them, so I'll get to see them in a bigger party.
Yeah.